Astronomy was previously an endeavor to attain enlightenment. For millennia, humans have examined the night sky, seeking to comprehend the nature of the cosmos we inhabit. Owing to the limitations of human perception, the majority of our ancestors were oblivious, and none grasped that the stars were other suns, and the planets were other worlds. Such disclosures depended on the invention of the telescope, a device that facilitated the observation of fainter and more distant celestial objects. Despite their restricted capabilities similar to modern toy telescopes, early telescopes revealed for the first time the moons of Jupiter, the craters on the Moon, and numerous fainter stars in the Milky Way. As telescopic power advanced, it was anticipated that telescopes, as devices for light collection, would reveal progressively more of the surrounding universe and ultimately unveil all its mysteries. Contemporary telescopes have obtained images of objects that nearly reach the confines of the universe and the thresholds of physical detectability. Absent the light-gathering capabilities of telescopes, our understanding of the universe might have been confined to the Milky Way, irrespective of the insights gained from their observations. The first truly modern telescopes, built on high mountains in the early 20th century, laid the groundwork for our story. In their elevated ivory towers, astronomers found themselves literally and metaphorically closer to the stars than ever before. These were thrilling times for astronomers. Our previously insular view of the universe, in which the Milky Way was the dominant feature, expanded to one where our galaxy occupied a subordinate role. Stars coalesced into galaxies, and galaxies merged into clusters of galaxies. The concurrent and autonomous discovery and elucidation of universal expansion prompted a collaboration between astronomers and physicists. Astronomers sought physical interpretations of their observations, while physicists regarded the universe as an expansive laboratory teeming with energy. Irrespective of the philosophical ramifications of these discoveries, or perhaps as a result of them, the future of astronomy seemed auspicious. Astronomers noted the night illuminated by the brilliance of innumerable stars at virtually inconceivable distances, while also observing the absence of a particular element. The stars and galaxies glimmered in the night sky, akin to moonlight on an ocean. However, their behavior was anomalous. Rather than congregating in the cold expanse of space solely dictated by their own gravity, the stars and galaxies seemed to be affected by mysterious, unseen forces that appeared to permeate the cosmos. Instead of controlling the universe, the stars and galaxies operated as mere components of a cosmic ocean. The problem is clear to understand, but difficult to address. The exclusive interpretation of gravity is the existence of matter. All entities in the universe exert gravitational forces on each other, a phenomenon that unifies solar systems, star clusters, and galaxies. The movements of stars and galaxies suggested the existence of additional matter beyond prior estimations. Nevertheless, when astronomers endeavored to ascertain the source of the gravitational force, they uncovered no information was provided. As larger telescopes delved deeper into space, they revealed structures of increasingly vast scales. Yet each observation exhibited the same perplexing gravitational phenomena. The broader the scale, from stars to galaxies to galaxy clusters, the more evident the mystery effect became. As astronomers conducted further observations, their comprehension of the universe diminished. The term missing mass was formerly employed to denote unseen matter because of its invisibility. However, this nomenclature is misleading, as its position is well defined, enabling astronomers to aim their telescopes at it. Despite the employment of the most advanced telescopes, it remains undetectable against the expanse of space, thus acquiring the label dark matter. However, this nomenclature undermines the significance of the concept it represents. The composition of dark matter remains unknown, rendering it one of the most profound cosmological enigmas. It is 100 times denser than observable matter. Is this merely a limitation of our fixation? Is this solely a limitation of our observational techniques regarding the universe? Initially, when scientists discovered dark matter, they were limited to observing the universe in visible light through optical instruments. In the last 70 years, the universe has been studied across various wavelengths, revealing previously undetectable phenomena, including interstellar gas and dust, neutron stars, radio galaxies, and black holes. Nonetheless, incorporating these previously unidentified matter sources does not fully clarify the impact of dark matter. We have been investigating the erroneous issue all along. Dark matter refers to non-luminous matter that does not radiate light. What if it consists of non-baryonic matter, entities distinct from the protons and neutrons forming stars and planets? We must examine non-baryonic matter, unidentified exotic particles. The universe's composition may significantly diverge from our own. This shift in our cognitive processes would not lack precedent. 4 centuries ago, the Copernican revolution displaced the Earth from the center of the universe. David Schramm advocates for a Copernican revolution, asserting that we are neither the focal point of the universe nor constituted of the same substance as the majority. Many candidates vie for classifying dark matter, neutron stars, primordial black holes, extinct stars, neutrinos, and various exotic particles referred to as WIMPs. We will evaluate these and additional candidates to observe how scientists strive to identify them. Nonetheless, we must proceed with caution concerning the conclusions we draw about the properties of dark matter. As creative storytellers, astronomers can develop a hypothesis from the existing data. Limited data allows for the theory's alignment. Astronomers must employ Occam's razor in their pursuit of a thorough comprehension of an astronomical phenomenon. The simplest and generally most elegant explanation should be prioritized. Concerning dark matter, it is advantageous to hypothesize a singular form of dark matter to elucidate the gravitational phenomena observed at both galactic and extragalactic scales. However, the development of our narrative suggests that the situation is more intricate than it seems. We may need to adjust to diverse forms of dark matter, each influencing the gravitational effects detected at varying scales. Regardless of its characteristics, dark matter undeniably influenced the universe's origin. Without it, the universe would be devoid of galaxies, stars, and possibly any entities to contemplate the rationale behind existence. Nonetheless, it possesses them. And here we remain. Like its essential role in the early universe, dark matter may influence the balance between cosmic expansion and gravitational forces. The discovery of dark matter coincided with the expansion of the universe, symbolizing the Big Bang, the primordial fireball that initiated the universe through the gravitational attraction of the matter it contains. If the universe has insufficient mass, it will continuously expand. However, if it has excessive mass, it will eventually collapse inward. Between these two extremes exists an optimal equilibrium of gravitational forces and expansion, a critical density, sufficient to cease the universe's expansion in an infinitely distant future. The total observable matter in the universe represents only a small fraction of the critical density. Could dark matter be the decisive factor? Is the universe influenced by an unusual force, such as the energy produced by the vacuum of space, which drives its continuous expansion despite the significant pull of dark matter? If correct, then the predominant composition of the universe is indeed dark matter. It's ironic that as telescopes grew larger and their detectors became more sensitive and broad in spectral range, they revealed not a universe rich in light, but one shrouded in darkness. not a universe ruled by visible stars and galaxies, but one dominated by an invisible, yet unidentified substance. The stars and galaxies may shimmer like jewels. This brilliance is only apparent in contrast to the velvety obscurity of dark matter. Notwithstanding their telescopes, detectors, and initial reservations, astronomers must contemplate a largely imperceptible universe. They continue investigating dark matter through telescopes, laboratories, and theoretical models. This exhaustive inquiry necessitates the contributions of some of history's most brilliant intellects and occupies substantial amounts of precious observational time on the globe's most advanced telescopes. It seems unusual to utilize telescopes to search for an invisible entity that emits no light. However, while these investigations revealed the external components of our solar system, the pursuit of dark matter will ultimately reveal the rest of the universe. Initially, it may have begun as a quest for enlightenment. However, astronomy has transformed into an investigation of the unknown. Dark matter is prevalent throughout the universe. Astronomers have discovered additional types of matter by analyzing the motion of galaxies and stars. The researchers found that dark matter is substantially more abundant than light matter by several hundred times. Researchers must exercise caution when claiming that dark matter seems to dominate, as scientific evidence is never definitive. Nonetheless, the evidence substantiating the existence of dark matter is persuasive. Improved methodologies now enable astronomers to examine the universe's complex phenomena with greater precision. They can now observe the movements of objects that are decreasing in size. We methodically measure time across scales from minute fractions of a second to the extensive duration of the universe's existence. We have scrutinized the observable universe across almost the entire electromagnetic spectrum, consistently revealing evidence of dark matter. What evidence suggests the presence of dark matter, especially in significant quantities? The solution lies in the disparity between the mass evaluations of the universe, luminous mass and gravitational mass. A discrepancy exists between the total mass of observable bright stars and galaxies and the mass indicated by their motion in space. This implies the existence of an undetected gravitational mass. Luminous and gravitational mass concepts are essential to the dark matter discourse. Thus, we investigate how astronomers measure the universe. A novel spectrum of gravitational waves, perturbations in spacetime, may soon be accessible for examination. Astronomers primarily employ the motion of stars or galaxies to determine a system's mass and subsequently compare that motion with the gravitational force necessary for the system's stability. Newton initially demonstrated that the combination of various forces could clarify the motion of objects. The resultant motion is the cumulative effect of multiple forces acting concurrently. In the realm of gravity, we have a law that epitomizes the nature of physical laws. Newton's principles are universally applicable across the cosmos. The balance between motion and gravity is often apparent and visually appealing, best understood through Newtonian principles of force equilibrium. Remarkable phenomena exist in our surroundings, such as the Moon, which orbits the Earth with mathematical precision due to its axial tilt, maintaining a linear trajectory facilitated by the Earth's gravitational pull. The numerous particles comprising Saturn's rings are extraordinary. The rings display such flawless symmetry that one might wonder why the particles do not revolve around the planet like a halo of moths surrounding a street lamp. Why do they not simply ascend into space or descend toward the planet? The conclusion is that multiple primordial particles that probably orbited Saturn either dispersed into space or merged with the planet. This transpired a significant time ago. What we observe today comprises only those particles caught in a delicate balance between the forces of motion and gravity. This identical equilibrium is evident in the clustering of asteroids within the asteroid belt and the spiral configuration of stars and gas in the Milky Way. Despite criticism of Newton's gravitational concepts as mere approximations, their significance should not be underestimated. They have demonstrated considerable success in revealing previously undetected masses across various scales. The first interaction with dark matter occurred in the outer solar system. While Newton's laws proficiently elucidated the motions of most known planets, they proved insufficient for the seventh planet, Uranus, whose erratic movements did not align with Newtonian gravity. Despite the various techniques celestial mechanicians utilized to refine their calculations, Uranus persistently strayed from its expected path among the stars. An issue has arisen. Is it possible that Newton's law of gravitation has a finite range, leading to its ineffectiveness beyond a certain distance from the Sun, thus allowing planets to move freely across the cosmos? This may be an overstatement, as the deviation between Uranus's observed location and its predicted location was analogous to the diameter of a human hair seen from a distance of 100 meters. Nevertheless, this negligible amount frustrated the astronomers of that period more than anything else. What was the origin of the error? Two gifted young individuals with an affinity for mathematics emerged. One individual was British, John Couch Adams. The other was French, Urbain, Jean-Joseph Leverrier. By the early 1830s, the irregular movements of Uranus had become so apparent that astronomers hypothesized the existence of an additional planet situated beyond the Sun. A planet of this nature would exert a gravitational force on Uranus, displacing it from its expected position. Adams was the first to accurately determine the mass of the undiscovered planet, its distance from the Sun, and its location in the celestial sphere. By October 1843, Adams had formulated a credible estimate of the new planet's celestial position. However, owing to petty elitism and interpersonal disputes, he failed to capture the interest of the Astronomer Royal, George Biddle Airy, leading to the unverification of his predictions. 2 years later, Leverrier performed calculations similar to Adams's across the English Channel, unaware of the previous discoveries. Leverrier completed his research on September 18, 1846, and communicated the results to the German astronomer Johann Gottfried Galle. Galle acquired a new compilation of star charts illustrating the area of the sky that included the expected position of the new planet. He initiated his quest for the new planet and located it just a few days later on September 23, 1846, within 1 degree of the position predicted by Leverrier. The discovery of the newly designated planet Neptune was a subject of considerable dispute. James Challis, who succeeded Airy as Professor of Astronomy at Cambridge, claimed to have discovered Neptune during his research, but did not have the time to verify his discovery, while Galle was the first to conclusively identify Neptune with a telescope. Ultimately, history has attributed shared recognition to Adams and Leverrier, despite Adams garnering scant attention during his contemporaneous era. David Blair and Jeff McNamara authored this report in Ripples on a Cosmic Sea. The investigation resulted in a substantial triumph for Newton's gravitational theory, as the laws of gravity accounted for even the minutest anomalies. Gravitation was universal, facilitating the analysis of the motions of remote and massive objects to explore the distribution of matter in the expansive universe. Nonetheless, advancements in understanding the universe at greater scales necessitated a reliable theory of gravity and improved observational techniques. Measuring the movements of stars presents a far greater challenge than evaluating the motions of planets, chiefly because of the substantial distance of stars from Earth. While traversing the freeway, you may have observed that the surrounding scenery alters your position. Regardless of speed, the forest and mountains advance gradually as you gaze toward the horizon. This phenomenon is termed perspective, culminating in the sky. Despite the Moon's 3,500 kilometers h velocity, It requires several minutes of observation to detect substantial movement against the background stars. The planets seem motionless at night, necessitating days, weeks, or months to move, by even a few degrees. Quantifying stellar movements is essential for analyzing the distribution of matter among them. Nevertheless, perspective suggests that even minimal displacement of a star may require years for accurate measurement. Nonetheless, astronomers achieved it in a rather ingenious manner. The path of a star in space is defined by 3 dimensions. One dimension is along the line of sight, and the other 2 are within the plane of the sky. The velocity of a star along the line of sight is ascertained through spectroscopy. When starlight from a single star or galaxy passes through a glass prism or similar device, it is dispersed and divided into its fundamental colors. A comparable phenomenon occurs when sunlight passes through rain, leading to the creation of a rainbow. The array of vivid hues, violet, blue, green, yellow, orange, and red, is termed a spectrum. When a star emits its spectrum adequately, it reveals a series of black lines resembling a barcode. Each spectral line signifies a specific chemical element in the star and occupies a unique predetermined position within the spectrum. Astronomers can determine a star's composition by examining its spectral lines. Light comprises electromagnetic waves, with each color associated with a specific wavelength, defined as the distance between the peaks of 2 waves. The location of a spectral line is defined by wavelength. Lines with shorter wavelengths are located nearer to the blue end of the spectrum, whereas those with longer wavelengths are found closer to the red end. The essential element of this narrative is that the motion of a star along the observer's line of sight causes a change in the apparent wavelengths of light. The alteration, manifesting as either an extended or diminished wavelength contingent upon the motion's direction, is attributable to the Doppler effect, which similarly accounts for the variation in pitch of a police car's siren as it approaches and recedes while one is driving on the highway. As the police car approaches, the siren's sound waves are compressed, yielding a higher pitch. Conversely, as it recedes, the waves are elongated, resulting in a lower pitch. The Doppler effect is relevant to starlight as well. The star will compress its light waves as it approaches you, resulting in any spectral lines exhibiting a shorter wavelength. This causes a transition toward the blue end of the spectrum. Conversely, a star moving away from you will stretch its light waves and shift its spectral lines toward the red spectrum. The blue or red shift of a star's spectral lines signifies whether the star is approaching or receding from you, respectively. Nonetheless, we can progress the concept further. The spectral lines shift by the star's velocity of approach or recession. The radial velocity of a star can be accurately determined by analyzing the position of the spectral lines in the visible spectrum. In the 1920s and 1930s, photographic techniques achieved remarkable precision. Stars move through the Milky Way at velocities of several hundred kilometers per second, and astronomers can measure these speeds with an accuracy of 1 to 2 kilometers per second. It's crucial to acknowledge that ascertaining the mass of a galaxy or galaxy cluster is a statistical endeavor. Therefore, observing a larger quantity of stars or galaxies improves precision. Modern astronomers markedly improved the assessment of stellar and galactic velocities by utilizing optical fibers in the final decades of the 20th century. These techniques facilitate the concurrent measurement of multiple variables. It is essential to acknowledge that the pioneers of the dark matter frontier were constrained to measuring the velocities of individual stars or galaxies, utilizing smaller telescopes and less sensitive detectors. Examining a star's motion, its radial movement toward or away from us, represents only a fragment of the entire story. To determine a star's true trajectory through space, assessing its motion along our line of sight within the celestial plane is crucial. This lateral motion represents the star's proper motion measured in a more direct, albeit significantly less precise manner. First, obtain an image of a star and determine its location. Thereafter, persevere for as long as possible. 1 year, 5 years, 10. The longer the duration, the more beneficial it becomes. Thereafter, re-evaluate the star's position and monitor for any displacement relative to other stars or galaxies. Despite its seemingly simple nature, it is complex and less accurate than radial velocity measurements due to the challenges in detecting minute movements across the sky. Astrometry conducted in space exhibits enhanced precision. The Hipparcos satellite has recently provided astronomers with extensive astrometric data on stars up to the 12th magnitude, nearly 250 times fainter than the dimmest star visible to the human eye. The results confirm the absence of dark matter in the Milky Way's disk. Astronomers expect the upcoming astrometric space mission, the European satellite Gaia, scheduled for launch in 2011, to provide astrometric data for around 1 billion stars down to the 20th magnitude. By acquiring a star's radial velocity and its transverse, or proper motion, one can ascertain its true three-dimensional motion through space, known as its space motion. Despite methodological advancements over the past century, accurately quantifying the spatial motion of stars remains a considerable challenge for astronomers. Examining stellar movements has been essential in clarifying the structure and determining the mass of the Milky Way galaxy. Upon observing a star system, one may question, what inhibits this structure from collapsing inward? Only the motions of the stars within a system like the Milky Way facilitate its expansion. This motion presents itself in two forms: average and random. All stars near the Sun display an average spatial motion primarily defined by rotation, as the Sun and other stars orbit the Milky Way. Nonetheless, it is not an entirely fluid motion. The stars traverse irregular circular trajectories akin to an inadequately deformed bicycle wheel, rather than in flawless circles. A typical star orbiting the Milky Way at roughly 8 kiloparsecs from the galactic center follows a nearly circular path. 1 kiloparsec is equivalent to 3,262 light-years. While orbiting the Milky Way, the star demonstrates a wobble in its circular trajectory, periodically nearing the galactic center and receding, with an amplitude of 0.5 to 1 kiloparsec. These oscillations are distinctly irregular. When situated near the Sun and observing transiting stars, one may notice that some oscillate inward, others outward, while some are at a critical juncture. The Milky Way demonstrates an average rotational motion, leading to its circular form, and exhibiting some erratic movement. Let us analyze these two types of motion, circular and random, in greater detail. In pure rotation, all entities traverse a circular trajectory. This requires an inward acceleration, determined by the square of the velocity divided by the radius. The internal gravitational pull depends on the position within the galaxy. The system attains ideal circular motion when each particle in a galaxy orbits at a velocity precisely corresponding to its radius, with the gravitational field supplying sufficient acceleration for circular motion. In such a system, stochastic movements are absent. Conversely, there exists a wholly stochastic system devoid of an average rotation, wherein all stars converge toward the galactic center and subsequently disperse in various directions. This system would consist of stars with varying energy levels distributed at diverse distances from the galactic center. The structure would be maintained solely by the arbitrary movements of the stars, analogous to the pressure in a gas. A galaxy of this type would resemble a swarm of moths surrounding a street lamp. In a true galaxy, it is undoubtedly a synthesis of both components. Like the Milky Way, spiral galaxies primarily demonstrate rotation with limited random motion, while elliptical galaxies exhibit greater random motion and reduced rotation. In every galaxy, three forces must achieve equilibrium. the gravitational attraction from the galactic center, the pressure resulting from the star's erratic motions, and the acceleration required for average circular motion. These three elements fluctuate according to their position within the Milky Way. In 1919, British scientist Sir James Jeans formulated a set of equations connecting these three variables. In the following film, we will examine Jeans' equations, a strictly qualitative analysis. However, it is essential to emphasize that these equations link mass and motion across various scales, from interstellar molecular clouds where stars form to the galaxies themselves. Jeans' equations illustrate the relationship between the average and random motions of stars, the gravitational force at a specific location in the Milky Way, and the stellar density in that region. Density refers to the quantity of matter contained within a specific volume. Astronomers have employed Jeans' equations to determine the mass of the Milky Way based on the observed motions of the stars. The mass is defined by the amount of gravitational force necessary to balance the motion of the stars. This is known as gravitational mass. The amount of gravitational mass is sufficient compared with the mass represented by the luminous matter in the Milky Way. During the initial decades of the 20th century, measuring visible objects was a rather indirect endeavor. Astronomers had an unclear comprehension of the various types of stars in the Milky Way. In 1924, British astronomer Arthur Stanley Eddington proposed a preliminary correlation between a star's mass and its absolute brightness, defined as the luminosity a star would display at a standard distance of 10 parsecs. Ultimately, empirical investigations of binary stars clarified this connection. The mass of a star is conventionally expressed in solar masses, with the Sun's mass designated as 1. However, one should not assume that the relationship between absolute brightness and mass is consistent among all stars. A large star displays significant luminosity, leading to a diminished mass-luminosity ratio. A considerable degree of brightness is contingent upon a particular mass. In contrast, diminutive stars, substantially smaller than the Sun, demonstrate a deficiency in luminosity relative to their mass. The mass-luminosity ratio is exceptionally elevated in this context. The mass-luminosity relationship for stars of differing brightness has been thoroughly investigated over the years and is now well comprehended for most stars in the Milky Way. Thus, by summing the masses of stars with differing luminosities in the ratios observed in the Milky Way, one can reasonably approximate the galaxy's luminous mass. This technique was initially utilized in the 1920s, and although modern estimates are frequently produced through theoretical methods, such as simulating virtual star populations via computational models, the outcomes remain predominantly consistent. A dilemma has emerged for astronomers studying the dark matter phenomenon. If only stars and gas were present, the gravitational and luminous mass of the Milky Way would be equivalent. Nonetheless, as you may have inferred, they are significantly different. Who is the discoverer, and who will be the subject of the ensuing film in our narrative? We must examine the past to clarify how observing stellar movements led to identifying dark matter. However, we must return to the 1920s, when our understanding of the universe's scale, attributes, and origins was rapidly advancing. This historical period corresponds to the early era of the telescope, when the universe shifted from a localized geocentric model to a paradigm in which Earth is merely another planet orbiting an ordinary star. By the 1920s, many astronomers adopted the galactic model proposed by Jacobus Cornelius Kapteyn in 1901, a large elliptical collection of stars with our solar system near the center. Although Kapteyn did not publish his theory for nearly 20 years, his contemporaries extensively acknowledged it, including the young Jan Hendrik Oort, whom we will soon discuss. Although Kapteyn's model was widely accepted, investigations by other astronomers, notably Americans Harlow Shapley and Heber D. Curtis, revealed that the Milky Way was considerably larger than Kapteyn's estimation. Researchers found that the unusual spiral-shaped nebulae once thought to be parts of the Milky Way are, in reality, immense galaxies situated at considerable distances from our galaxy. Astronomers, including Vesto Melvin Slipher and, subsequently, Edwin Hubble, conducted additional observations employing techniques akin to those utilized in the spectral line observations depicted in the preceding film. Most galaxies displayed a redshift, indicating their retreat from the Milky Way. This discovery demonstrates that the universe is expanding, with each galaxy receding from all others, rather than implying that the Milky Way holds a central position in the universe. Envision sultanas in a fruitcake baking in an oven to exemplify the reciprocal recession of galaxies. As the cake rises, each sultana detaches from the others, driven by the expanding cake. Although Hubble identified the phenomenon of universal expansion, it is crucial to note that his observations of receding galaxies were preceded by Slipher, the leading authority on galactic velocities at that time. Hubble identified a fundamental principle that associates distance with recession velocity. The reciprocal recession of galaxies indicates that a galaxy's recession velocity from an observer correlates positively with its distance. Examine 3 galaxies evenly distributed along a linear path, all moving away from each other at the same velocity. Imagine our existence in a galaxy located at one end of the continuum. As we depart from the intermediate galaxy, we will also distance ourselves from its inhabitants. However, the recession of the more distant galaxy, located twice as far away, would transpire at twice the velocity of the nearer galaxy. This transpires as it recedes from the nearer galaxy, which is simultaneously distancing itself from us. A galaxy's recession velocity increases with its distance. The recession velocity is proportional to distance, yielding a nearly constant velocity-to-distance ratio across various galaxies. Determining the Hubble constant has emerged as a considerable challenge. A principal reason is the significant challenge in precisely measuring distances to galaxies. Hubble afforded scant attention to the theoretical foundations of the universe's possible expansion. As Hubble and Slipher studied the receding galaxies, several theorists, including Albert Einstein, developed a theoretical model for an expanding universe. An important implication of an expanding universe is that all existence began at a particular moment in the past. This event is termed the Big Bang and is crucial to our account of dark matter. We will analyze its complexities in greater detail later. Jan Hendrik Oort, a prominent figure in 20th century astronomy, emerged during this discovery period. However, contemporary consensus deems his conclusions about dark matter incorrect. Oort, more than any other individual, inspired astronomers to seriously consider dark matter on a galactic scale. Notwithstanding his diminutive stature, Oort was an imposing figure with a commanding presence. During World War II, he refused to cooperate with the German authorities and resigned from his position at Leiden University to continue his studies from a cottage in the Dutch countryside. Oort attained international recognition and wielded significant political influence in the Netherlands from an early age. After his retirement, he pursued his studies almost until his death at 92, and maintained his proficiency in ice skating well into his 90s. The Netherlands has a profound and lasting heritage in astronomy, which Oort sustained and guided. In 1935, he became a professor of astronomy at Leiden Observatory during the early development of radio astronomy in Australia and the United States. He cultivated an increasing fascination with radio astronomy, acknowledging that radio waves could penetrate the obstructive gas and dust clouds of the galaxy, and the atmospheric clouds commonly found in Dutch skies during most evenings. Thus, it is not unexpected that following the Second World War, he and his colleagues obtained a German 7.5-meter radar dish, converted it into a radio telescope, and utilized it for groundbreaking research. Henk van der Hulst, a protégé of Oort, predicted the emission of the famous 21-centimeter spectral line of neutral hydrogen. Astronomers in Leiden initially identified hydrogen gas in the Milky Way's interstellar medium, enabling the analysis of its rotation. The investigations carried out by astronomers in the United States and Australia confirm the long-standing hypothesis concerning the spiral structure of the Milky Way. These insights were of historical significance. Oort acknowledged that the Netherlands needed a modern radio telescope substantially larger than the 7.5-meter German antenna that had been utilized. In 1956, he was instrumental in establishing a 25-meter antenna at Dwingelo in northern Netherlands. And in 1970, he aided in the development of the Westerbork radio synthesis telescope. The Westerbork instrument is a large interferometer comprising 14 25-meter dishes, positioned along a 2.8-kilometer east-west axis, similar to the Australia Telescope Compact Array, ATCA, but larger and more powerful. We will illustrate that the Westerbork telescope was pivotal in guiding astronomers to comprehend that spiral. Galaxies primarily comprise dark matter rather than stars. In conclusion, Oort's influence in this field was significant. Nevertheless, we should return to the account of his previous research. An important initial finding from the study of stellar movements was the rotation of the Milky Way. Between 1925 and 1930, three notable figures, Gustav Stromberg, Bertil Lindblad, and Jan Oort, played a significant role in discovering the galaxy's rotation. Stromberg's contribution involved identifying a correlation between the average motion of Milky Way stars and their random motions. The greater the random motion of a specific class of star, the higher their average velocity relative to the Sun. The erratic movements of stars function similarly to gas pressure, and in conjunction with rotation, they sustain the galaxy's stability against its own gravitational pull. Stromberg's discovery furnished substantial evidence that we reside in a rotating galaxy. Lindblad was the first to establish that the Milky Way is rotating, with stars tracing nested orbits around the galaxy's center, similar to the planets orbiting the Sun, though more intricate. Lindblad's mathematical works inspired numerous astronomers, including Oort, to explore stellar migration within the galaxy. Oort's contribution was the discovery of the galaxy's asymmetrical rotation in 1927. He acknowledged that the disk-shaped galaxy did not rotate uniformly like a car's wheel, where all components revolve for the same duration. Rather, the inner sections of the galaxy rotated more swiftly than the outer regions. Every location in the galaxy possesses a unique angular velocity, making the movement of stars and gas in the Milky Way comparable to the vortex created as bathwater drains into a plug hole. Notwithstanding its simplicity, this accomplishment was noteworthy when we had not yet confirmed the galaxy's structure, particularly its spiral arrangement. In 1932, Oort's interest in galactic dynamics resulted in a comprehensive examination of the matter within the galaxy's disk. Kapteyn and Jeans had previously expressed skepticism regarding unseen matter in the Milky Way. However, Oort undertook the first extensive examination. Oort examined the average, random, and perpendicular motions of stars within the Milky Way to evaluate the matter density of its disk. Stars revolve around the galactic disk while concurrently oscillating vertically through the plane of the galaxy, similar to toy horses on a carousel. Stars' average rotational and random motions impede their collapse towards the center of the galaxy, while their vertical motion prevents the galaxy from assuming a completely flat disk shape. One of Jeans' equations relates the average rotational motion, random motion, and gravitational force within the galactic plane. Another Jeans equation relates the vertical motion of stars to the gravitational field of the disk. The gravitational pull, drawing all stars toward the galactic plane, is offset by the random vertical movements of the stars, which operate akin to pressure in a gas. Oort was convinced he had detected dark matter in the disk and was analyzing vertical stellar motions. However, this undertaking was challenging. an error transpired in Oort's circumstance. Examine the star's irregular vertical motions and their alignment perpendicular to the disk to determine the matter density of the disk. Nonetheless, the Jeans equations are quite specific concerning the stars in the analysis. It is essential to employ identical stars to acquire precise density and velocity data. Otherwise, the results will be erroneous. This is where Oort made an error. Astronomers determined the vertical distribution of stars relative to the galactic disk by enumerating all visible stars within a designated sky area that constituted a vertical column to the disk. They examined the spatial configuration of the stars within the column by assessing their luminosity distribution. Observing a greater quantity of luminous stars than dim stars indicates a higher density of stars located nearby rather than at a distance. A deficiency of bright and faint stars, alongside a surplus of stars of intermediate brightness, signifies the existence of a layer of stars at a specific intermediate distance, and so on. This neglects crucial factors, especially since not all stars have identical intrinsic luminosity. Furthermore, it neglects to account for the interstellar dimming, caused by dust along the line of sight. We evaluated the vertical motions of the stars employing the Doppler effect. In the 1920s and 1930s, astronomers, lacking sophisticated detectors, spectrographs, and large telescopes, were compelled to choose the most accessible stars for measurement. K giants are especially attractive to astronomers for velocity measurements. The letter K derives from the esteemed Hertzsprung-Russell diagram, which contrasts a star's luminosity with its spectral temperature. These aged stars have exhausted most of their hydrogen reserves and expanded to considerable dimensions, typically 30 times the Sun's diameter, rendering them approximately 100 times more luminous and consequently more discernible. Equally important, they are cold stars, with many easily identifiable spectral lines for measurement. Hot stars generally display fewer spectral lines for reasons unrelated to this discourse. Oort posited, as did all astronomers until the 1980s, that these K giants were indicative representatives of the galactic disk. Nevertheless, they are not. The galaxy's disk is complex, comprising the thin disk visible in edge-on spiral galaxy images and a more diffuse structure termed the thick disk, which was recognized in 1983. The thick disk is approximately 4 to 5 times more voluminous than the thin disk and is recognized for its abundance of ancient stars, including the easily recognizable K giants. The stars in the thick disk presumably originated during the galaxy's primordial phases. One complication that perplexed Oort's estimates was that the stars in the thick disk typically exhibit double the random velocity of those in the thin disk, which explains the increased thickness of the thick disk. These robust, thick disk stars masqueraded as thin disk stars and infiltrated Oort's calculations. Their heightened vertical movements likely affected his claim that the star's average vertical motion within the galaxy's disk was greater than it truly is. Oort deduced that the disk's significant average vertical motion indicates the presence of substantially more matter, potentially double that of the stars in the Milky Way, to maintain its cohesion. If such a substance existed, it was completely devoid of light. Oort continued his research on disk dark matter throughout the 1940s and 1950s. The subject remained dormant until the 1970s, when American astronomer John Barkall, leader of the astrophysics group at the Institute for Advanced Study in Princeton, performed a similar analysis to Oort's utilizing more recent data. Barkall's findings largely aligned with Oort's, yet they stimulated extensive investigations into disk dark matter. The notion of dark matter in the peripheral areas of galaxies has become widely accepted, prompting considerable interest in ascertaining the presence of dark matter within the disks of galaxies. This signified the commencement of the conclusion regarding disk dark matter. Subsequent independent studies consistently produced disk dark matter values that were inferior to those of Oort or Abell. In 1988, a notable setback for disk dark matter transpired when Konrad Kuijken, a Belgian student working with Jerry Gilmore at Cambridge, published a crucial series of papers in the monthly notices of the Royal Astronomical Society, suggesting that there was negligible, if any, dark matter in the Milky Way's disk. The varying conclusions regarding disk dark matter are partially attributable to an improved mathematical approach for calculating the gravitational mass within the galaxy's disk. The Jeans equations, utilized by prior researchers, derive from the more fundamental Boltzmann equation, which relates to phenomena in both spatial and velocity domains. The Boltzmann equation employs a density d characterized in six-dimensional space, rather than specifying that a particular region contains a certain number of solar masses per cubic parsec in three-dimensional space. This indicates the subsequent. We reside in a specific location within the galaxy and seek to ascertain the density of solar masses per cubic parsec. In this context, we seek to ascertain the density in velocity space. What is the measure of solar masses per cubic parsec or per cubic kilometer per second? The phase space density, denoted as F, measures the quantity of stars possessing a particular velocity within a specified spatial volume. The Boltzmann equation describes the variation in density as a function of velocity and position, thus dependent on gravitational force. The phase space density thoroughly defines the star system, making it a more fundamental equation. Despite its limitations, this technique bypasses specific variables of the Jeans equations that are difficult to quantify. Most astronomers argue that the Milky Way's disk, contrary to Oort's claim, is predominantly lacking in dark matter. A 1998 study conducted by Olivier Bianem and colleagues in France substantially corroborated this conclusion. Utilizing the densities and movements of stars recorded by Hipparcos, they illustrated that the gravitational density of the disk closely resembles that of observable entities. This does not inherently indicate the end of disk dark matter. Instead, the dominant view is that there is little, if any, dark matter in the disk. The existence of dark matter in the disk would greatly simplify astronomical studies by clarifying numerous observed phenomena. The lack of dark disk matter presently causes the Milky Way's disk to be less massive than that of most analogous galaxies. This is an ongoing issue. Is our galaxy anomalous? Or are certain methodologies utilized for measuring other galaxies defective? Many astronomers find the absence of dark matter in the disk disconcerting and advocate for its presence roughly twice the existing quantity. Despite appearing erroneous, Oort's discovery of disk dark matter would produce a considerably more acceptable result. Despite widespread contrary belief, astronomers are uncertain about the validity of the prevailing conclusion that the disk contains no dark matter. Furthermore, ancillary and confounding elements arise. Nonetheless, Oort's erroneous conviction in disk dark matter was not a deceptive hypothesis for two reasons. Initially, it facilitated the improvement of the existing galaxy model. In 1922, Oort analyzed the motion of vast spherical collections of stars, referred to as globular clusters within the galaxy. Most galaxies, including the Milky Way, contain compact collections of roughly 1 million stars, known as globular clusters. Oort concluded that the gravitational influence of luminous matter alone cannot retain globular clusters within the galaxy due to their swift motion. A fundamental star chart demonstrates that globular clusters aggregate at the galaxy's center, aligned with the constellation Sagittarius. The uneven distribution in the sky indicated to Oort that the globular clusters are integral to the galactic system rather than merely traversing it. Kapteyn's hypothesis posits that the galaxy must have a mass 200 times that of its stars to sustain their observed velocities. This sparked interest in the notion of unseen dark matter and necessitated a reassessment of the dimensions and configuration of the Milky Way. Secondly, the episode conveys a crucial lesson about the nature and approach of science. Decades following Oort's assertion, dark matter comprised half of the galaxy's disk before further astronomical inquiries into the matter. It is reasonable to expect that a substantial discovery by a distinguished astronomer would attract considerable attention from the scientific community and incite further inquiry. The reasons for the absence of follow-up remain conjectural. At that time, traditional astronomical discourse did not incorporate the concept of dark matter. Nonetheless, astronomers considered Oort's discovery to be overly significant. His dominance was so pronounced that astronomers believed they could not exceed his published findings. Bacall's reassessment of the matter revealed Oort's error. The conclusion is to refrain from placing undue trust in any result, irrespective of the prominence of the scientist who generates it. Science thrives and progresses through doubt and skepticism. In their absence, it becomes inert. Despite its initial deficiencies, Oort's research and distinguished reputation as a leading scientist stimulated the concept of dark matter on a galactic scale. Shortly after he announced the presence of dark matter within the galactic disk, one of his colleagues disclosed its existence on a more extensive scale and in significantly larger quantities. Only the divergence between the two individuals corresponds with Oort's findings. Following Oort's assertion of dark matter in the Milky Way's disk, astronomer Fritz Zwicky announced its existence in distinct galaxies and galaxy clusters. At a time when the majority of astronomers failed to perceive our galaxy as merely a typical assemblage of stars akin to other galaxies in the universe, Zwicky was already acknowledging that the cosmos comprised thousands of galaxies, featuring vast structures and peculiar phenomena, such as neutron stars and dark matter. Zwicky was an outstanding scientist who contributed substantially to astronomy and other disciplines. He was born in Bulgaria to Swiss parents and spent most of his professional life in the United States. After earning a PhD in physics from the Swiss Federal Institute of Technology, Zurich, in 1922, he moved to the United States and served as a faculty member at the California Institute of Technology, Pasadena, from 1925 to 1972. Despite his residency, he faced a denial of American citizenship in 1949. Zwicky's astronomical accomplishments extend beyond the simple discovery of large-scale dark matter. In 1934, he clarified the difference between novae and supernovae in collaboration with Walter Bardy. They established that supernovae occur considerably less frequently than novae, and correctly posited that supernovae result from the death of massive stars. They proposed that the consequence of a supernova explosion would consist solely of a neutron star. Appendix 1 offers a detailed account of the neutron, a diminutive neutral particle found in the nucleus of most elements. Discovered in 1932 by James Chadwick, it is reported that shortly after learning of the discovery, the prominent Russian physicist Lev Landau conceived of an exceptionally compact and dense star predominantly composed of neutrons. Bardy and Zwicky elucidated how an ordinary star can transform into a neutron star 2 years later. The narrative they recounted remains fundamentally unchanged today, albeit with certain modifications. All stars are spherical entities comprised of heated gas. Despite its immense size, the ongoing energy output from the star's core maintains its spherical form against gravitational forces. This energy derives from the fusion of lighter elements with their heavier counterparts. Provided with nuclear fuel, such as hydrogen in the case of the Sun, a star can maintain its resistance against the inward force of gravity. Ultimately, all stars exhaust their nuclear fuel, leading to the cessation of energy emissions. A diminutive star of solar mass experiences a relatively serene demise. Without external support, its core collapses into a white dwarf, roughly the size of Earth. while the outer layers are ejected into space, forming a magnificent planetary nebula. In contrast, a more massive star ends its life more dramatically. Depleting its nuclear fuel supply, it undergoes a dramatic implosion. The substantial implosion results in a core bounce, triggering the detonation of most of the star's outer layers. With the brightness of 1 billion stars, the stellar core continues its descent concurrently. With a mass similar to that of the Sun, the core would compress to a diameter of about 20 kilometers. At this density, electrons and protons would combine to form neutrons, leading to a thimble-sized volume of the substance weighing 100 million tons. Confirming Zwicky and Bardé's hypothesis would necessitate an additional 35 years. Zwicky predicted that dark matter in the universe could be identified through gravitational lensing, a topic that will be explored in detail later in this book. The core principle is that the gravitational fields of massive bodies can modify the path of starlight. The concept is based on Einstein's general relativity prediction that light follows the local curvature of spacetime surrounding a massive object. The esteemed British astronomer Arthur S. Eddington corroborated Einstein's prediction during a significant expedition to observe the deflection of starlight during the total solar eclipse of 1919. Notwithstanding the expedition's success and the confirmation of Einstein's prediction, which elevated him to unexpected prominence, both Einstein and Eddington doubted the phenomenon's practical applicability in scientific research. One possibility was the concept of gravitational lensing, wherein the gravitational field of a galaxy distorts and amplifies the light from more distant galaxies, analogous to how a magnifying lens concentrates sunlight, a phenomenon well known to children, often to the detriment of unsuspecting insects. Despite Einstein and Eddington's skepticism regarding the likelihood of alignment, Zwicky believed that gravitational lensing could be advantageous for investigating phenomena at the farthest reaches of the universe. His prognosis was exceptionally significant. We will illustrate that gravitational lensing is extensively utilized in the search for dark matter within galaxies and galaxy clusters, yielding significant success. Besides these contributions, Zwicky researched cosmic rays and the advancement of early jet engines. Few scientists possess intellects decades ahead of their peers, yet Fritz Zwicky exemplified this remarkable trait. Personally, he was an articulate individual with a distinct accent despite residing in the United States for nearly 50 years. He was flamboyant, self-centered, and contemptuous toward many colleagues. One of his favored insults was designating disapproving individuals as spherical bastards. Regardless of the perspective, he asserted, they remained bastards. Zwicky was chiefly an observational astronomer and engaged in substantial theoretical research. He was one of the first individuals to establish that the observed concentrations of galaxies, initially observed by Herschel, were in fact authentic clusters. He detected multiple galaxy clusters using the 48-inch Schmidt telescope at Mount Palomar Observatory. For example, when the total number of supernova discoveries reached 12 from 1937 to 1941, Zwicky identified an additional 18 in various galaxies. In his later years, he amassed comprehensive catalogues of galaxies. However, his resentment endured. As he became more resentful of the external world's treatment of him, he wrote a scathing foreword to his 1971 catalogue of selected compact galaxies and post-eruptive galaxies, parts of which are engaging to read. Several examples are presented here. The naivety of certain theorists is perpetually astonishing. We need only cite the distinguished American astronomer Henry Norris Russell, who in 1927 stated, "The characteristics of the stars are dependent on the most basic and fundamental laws of nature, and even with our present knowledge could have been predicted from general principles had we never observed a star." Henry Norris. Russell was a distinguished astronomer who made substantial contributions to stellar astronomy, and most modern astronomers would probably not dispute his assertion. Zwicky was clearly exasperated by his failure to employ the Mount Palomar 200-inch telescope until the latter stages of his career. He created. The most distinguished observational astronomers of the 1930s made claims that were subsequently demonstrated to be wholly erroneous. Consequently, E.P. Hubble, W. Bardet, and their youthful adherents seeking camaraderie altered their observational data, concealed their deficiencies, and persuaded the majority of astronomers to concur with their biased and erroneous representations and interpretations of facts. Like various other human pursuits, astronomy has persistently faced disruption from influential figures within its hierarchical frameworks. The excessive material in the abundant astronomical journals offers persuasive proof. Zwicky consistently chose distinguished subjects for his critique. Hubble and Bardet were instrumental astronomers of their time, and their findings concerning the universe's expansion and the classifications of stars within galaxies are undeniably consequential. The editors of the Astrophysical Journal exhibited a remarkable deficiency in tolerance and discernment when they rejected my initial comprehensive and observationally substantiated article on compact galaxies. This sharply contrasted with their uncritical acceptance of juvenile fantasies and appropriated concepts. This coincided with the discovery of quasars, highly luminous and distant entities. Zwicky's peers occasionally reflected on his contempt. He wrote a book entitled Morphological Astronomy, which clarified morphological arguments for employing patterns to determine the nature of entities. The book thoroughly presents the diverse perspectives he has developed over the years. Nevertheless, it contains multiple insights that remain pertinent in modern times. Initial instances of composite imaging illustrate the distribution of various star types within a galaxy. By superimposing a negative print of the galaxy in one wavelength band, such as yellow light, over a positive print in another wavelength band, such as blue light. Nevertheless, the majority of individuals disregarded this book. His book was classified in the fiction section of an observatory library regularly visited by Zwicky, except during his own visits, when it was relocated to Z in the science section. Zwicky boldly addressed major astronomical questions and was determined to determine the mass of extragalactic nebulae, galaxies, and galaxy clusters. In approximately 1933, he published his first works on these subjects in German. In 1937, he published a detailed paper in the Astrophysical Journal outlining the fundamental principles of mass measurement that would be investigated over the next 60 years, including the virial theorem, a method for calculating the mass of a galaxy or galaxy cluster, which will be elaborated upon shortly. He clarified the methodology utilized to detect dark matter in galaxy clusters. Similar to inferring a galaxy's mass from its gas and stars, we can ascertain the mass of a galaxy cluster through their motions. Zwicky's investigation of galaxy clusters presented an innovative approach to measuring mass in the universe. A significant sample is crucial for analyzing the behavior of galaxies within groups, and certain galaxy clusters are particularly appropriate for this purpose. The history of galaxy clusters commences with William Herschel, who, in the 1780s, noted that galaxies, then termed nebulae, were not randomly dispersed in the sky, but appeared to congregate in groups. Herschel observed a specific cluster within the constellation Virgo. In 1933, Harlow Shapley published a compilation of 25 galaxy clusters. He claimed that the groups were not mere coincidences, but the result of an evolutionary process. His investigation of Cepheid variable stars in globular clusters advanced the understanding of the Milky Way's dimensions. Before the 1950s, most astronomers perceived galaxies as isolated entities, with only a limited number demonstrating authentic physical connections with others. Nevertheless, evidence suggesting that galaxies exhibited sociability began to amass. In 1958, George Abell published a catalogue of 2,612 galaxy clusters. From 1960 to 1968, Zwicky and Associates released catalogues of 9,134 galaxy clusters. These notable works were generated by examining the photographic plates obtained with the 48-inch Schmidt at Palomar, compiled into the National Geographic Society Palomar Observatory Sky Survey, POSS. The substantial discrepancy in the galaxy count results from the divergent methodologies utilized by the two astronomers in their classification of clusters. Abell concentrated solely on the most densely populated clusters, while Zwicky encompassed all aggregates, irrespective of their sparsity. Subsequently, enhanced observational techniques and statistical methods have revealed that most galaxies exist within groups and clusters, with only a minority residing in isolation within the universe. Galaxies display diverse shapes and sizes. We reside in a flattened disk defined by an internal spiral arrangement. Spiral galaxies are generally rich in gas, dust, and stars, and categorized into classic spirals that resemble cream swirling in freshly mixed coffee, and barred spirals characterized by central bars from which the spiral arms extend. In contrast, elliptical galaxies lack internal structure, contain minimal gas or dust, and appear flattened spheres. Ultimately, the gas-rich galaxies, designated as irregular due to their ambiguous morphology, are observed. The small Magellanic cloud serves as a prime example of this category. In 1925, Hubble proposed a system to classify galaxies systematically. Although the origins of various galaxy types remain uncertain, recent observations of distant galaxies, those existing during the universe's inception, reinforce the correlation between morphology and galactic evolution. Morphology can classify individual galaxies, but distinctive characteristics differentiate galaxy clusters. Abell and Zwicky were the forerunners in classifying these types of clusters. Abell classified them as regular or irregular, while Zwicky categorized them as compact, medium, or open. Neither classification system accounted for the types of galaxies within clusters based solely on the spatial distribution of the constituent galaxies. William W. Morgan was the inaugural researcher examining the distinct clusters' attributes. He rigorously analyzed multiple neighboring galaxy clusters, focusing on the more luminous constituents within 2 magnitudes of the brightest member. He identified 2 groups. One predominantly comprised spiral galaxies, with only the most luminous being elliptical or S0, flattened like spirals but with minimal gas, while the other exhibited greater density, featuring exclusively elliptical or S0 galaxies among the brightest, accompanied by a few fainter spirals. Analogous to solitary galaxies, these characteristics demonstrated a correlation between a cluster's morphology and its environment. We presently classify galaxy clusters as either regular or irregular. Regular clusters are nearly spherical assemblages of galaxies, primarily consisting of elliptical or S0 galaxies. They are wealthy and dense, possibly comprising 5 to 10% of the galaxies in the universe. Irregular clusters possess no discernible shape and may include any galaxy. These clusters are dense and resemble aggregations of smaller clusters, comprising between 10 and 1,000 galaxies, whereas smaller clusters, approximately 3 million light-years in diameter, are more common. Researchers have identified numerous clusters of galaxies and conducted studies on them. This has facilitated their understanding of galaxy formation and evolution, high-energy astrophysics, large-scale structures, and cosmology. The cluster employed by Zwicky for his dark matter research is designated as 1656 in Abell's catalogue, and is situated roughly 90 megaparsecs away in the northern constellation of Coma Berenices. Known as the Coma cluster, this vast and affluent cluster was first recorded by Max Wolf using the Bruce telescope in Heidelberg, Germany in 1901. The nearly spherical structure is divided into 2 components, each approximately equal in size and centered around a galaxy linked to a radio source. The Coma cluster is an ideal subject for observation. It is situated in a region of the sky remote from the plane of the Milky Way, thus remaining unimpeded by stars, gas, or dust. In 1957, Zwicky catalogued 804 galaxies, with magnitudes greater than 16.5 within approximately 2.5 degrees of the cluster's nucleus, and 29,951 galaxies exceeding magnitude 19 within 6 degrees. These galaxies are unconnected to the coma cluster. However, the system is anticipated to encompass over 1,000 galaxies, placing it within the top 5% of Abell's clusters by this metric. The coma cluster's primarily elliptical and S0 galaxies are believed to be among the earliest to have emerged in cosmic history. The cluster is dominated by two substantial elliptical galaxies, NGC 4889 and NGC 4874. They may have expanded significantly by consuming smaller galaxies throughout their extensive lifespans. The prior film demonstrated how Oort and others measured the Milky Way's mass by examining its constituent stars' velocities. Notwithstanding the considerable disparities in size and mass, evaluating a galaxy cluster's mass remains analogous. A notable distinction is that in a galaxy cluster, the primary motion is not rotation, but the random motion of the galaxies. Fortunately, a multitude of solutions is available to address these motions. A cluster operates analogously to the gas pressure within a distended balloon. The balloon remains inflated due to the balance between the random motion and pressure of the internal air molecules and the tension of the external rubber. Similarly, an elliptical galaxy or a galaxy cluster is maintained by the pressure produced by the motion of its constituents, stars within a galaxy or galaxies within a cluster, that counterbalances the inward force of gravity. The pressure can be measured by evaluating the velocity of galaxies within a cluster, enabling the calculation of the necessary gravitational field and associated mass required to contain the galaxies. The task becomes challenging due to establishing particular assumptions about the degree of random motion. For instance, a unique mass number would be acquired if each galaxy moved radially toward and away from the cluster's center. Nonetheless, that would represent an unusual situation, as most galaxies do not follow a radial orbit that directly intersects the cluster's core. Some follow circular trajectories, while others adhere to radial orbits. However, most navigate the cluster through diverse combinations of these extremes. As a result, the orbital configurations vary unpredictably. Another factor to consider is that systems like gas clouds or galaxy clusters exemplify a balance between gravitational forces and pressure, as well as between gravity and the pressure gradient, specifically the change in pressure relative to distance from the system's center. Pressure differentials do not exist when pressure is consistent across the system. A pressure force applies an outward thrust when the central pressure surpasses that of the surrounding regions. An illustrative instance is a solitary star, where the core pressure substantially surpasses that of the outer layers. The pressure gradient of the gas applies an outward force on the star's mass, striving to induce expansion, while gravity opposes this effect. Furthermore, organizing all system components, gas molecules or galaxies within a cluster, is essential when evaluating a pressure gradient. Notwithstanding the nebulous definition of galaxy clusters, one can analytically determine an average radius for a cluster, facilitating the computation of the pressure gradient within the cluster. Zwicky examined the trajectories of more than 600 constituent galaxies to determine the random motions within the coma cluster. Detecting any movements of the galaxies in the cluster along our line of sight is impractical due to their considerable distance, as the perspective at such ranges is extreme. By examining the Doppler shift in the spectral lines of multiple galaxies, he ascertained their velocities about the collective motion of the entire cluster. This task was laborious and was difficult at that time. The coma cluster is moving away from us at an average velocity of 7,000 km/s. This represents an average velocity akin to a swarm of bees departing from our location at a specified rate, Some bees will disperse more swiftly than others at any given moment based on their activity within the swarm. The motions of galaxies within the coma cluster suggest that certain galaxies are receding from us at greater velocities than others, despite the overall recession of the entire cluster. If a galaxy in the coma cluster is receding from us at 5,000 km/sec, it is approaching us relative to the cluster at 2,000 km/sec. Similarly, if we detect a galaxy moving away from us at 9,000 km/sec, it departs from the cluster's center at a 2,000 km/sec velocity. Neither of these galaxies, however, will detach from the cluster any more than the stars identified by Oort will detach from the Milky Way. The cluster's gravitational field is strong enough to capture potential escapees. Gradually, the cluster's gravitational field is adequate to modify the galaxy's orbits and draw them toward the core. Notably, greater disparities in speeds, indicative of the system's total kinetic energy, require additional gravitational energy to maintain the cohesion of the galaxies. The necessity of matter for gravity allows a direct comparison between kinetic and gravitational potential energy, thereby revealing the system's mass. As previously mentioned, despite the considerable difference in scale between an individual galaxy and a galaxy cluster, the relationship between kinetic and gravitational potential energy is a common element in studying dark matter at both the galactic and cluster levels. The calculation is more intricate for irregular systems like galaxy clusters, where movements are less defined. Zwicky determined the gravitational mass of the coma cluster utilizing a technique known as the virial theorem, which is founded on the Jeans equations previously employed by Oort. This illustrates the distinction between the kinetic energy a system possesses due to the motion of its components, such as galaxies within a cluster, and the gravitational potential energy required to maintain the system's structural integrity. Zwicky calculated the mass associated with each galaxy by employing the gravitational mass of the coma cluster. His accuracy may have been compromised, as scientists of that era were uncertain regarding the mass of individual galaxies and their stars, a challenge that still endures. Zwicky quantified the luminosity of each galaxy in his images, and formulated a reasonably accurate estimation of the cluster's overall brightness. This parallels the approach taken by Oort and others, who posited that the luminous mass of a galaxy could be determined by enumerating the stars and employing the stellar mass-luminosity relationship. Astronomers continue to utilize his hypothesis that the stellar composition of each galaxy is comparable. The procedure was intricate. Evaluate the luminosity, speed, and location of individual galaxies within a cluster, then deduce the luminous mass of the cluster. Zwicky discerned a distinction between luminous and gravitational masses during his analysis. If the cluster had contained only luminous matter, the velocities of the individual galaxies would have sent them to the far reaches of the universe long ago. This was clearly not the case. Some force applied adequate gravity to preserve the cluster's cohesion. Nonetheless, the volume of material involved was extraordinary, so substantial that it necessitated decades for the astronomical community to fully recognize Zwicky's discoveries. Numerous individuals were astonished when Oort asserted that the galaxy could possess double the amount of visible matter compared to stars. Zwicky's research, conversely, demonstrated a significant disparity between the visible matter and the matter exerting gravitational influence. His estimates suggested that the coma cluster contained almost 50 times the luminous material in an undetected state. Dark matter pervaded the coma cluster. 1933, Zwicky conducted this research, followed by Sinclair Smith's analogous experiment on the Virgo cluster at Mount Wilson Observatory 3 years later. This galaxy cluster is markedly nearer and displays an irregular morphology. The Virgo cluster, owing to its substantial mass and proximity, is drawing our minor group of galaxies. The local group of galaxies consists of two major spiral galaxies, the Milky Way and the Andromeda galaxy, and various dwarf, elliptical, and irregular galaxies. Like countless historical and potential galaxies, our galaxy may eventually succumb to the Virgo-centric flow and assimilate into it. The central region of the Virgo cluster is predominantly defined by a substantial elliptical galaxy, while the majority of the cluster's detectable mass comprises a hot gas with temperatures between 10 and 100 million degrees that permeates the cluster. Smith disclosed the hidden mystery of the Virgo cluster. By performing similar calculations on the Virgo cluster as Zwicky did for the Coma cluster, he concluded that it contained an exceptional 100 times more dark matter than luminous matter, presumably located between the galaxies. The virial theorem offered a persuasive justification for the presence of dark matter. After Zwicky's investigation of the Coma cluster, researchers have utilized the identical methodology on various other clusters, yielding comparable results. Astronomers were finding that the universe was becoming progressively obscure and enigmatic instead of clarifying its nature. Astronomers utilize arguments that surpass Zwicky's original propositions. For the last 25 years, Oort's dark matter hypothesis has impacted astronomers more than Zwicky's, despite the latter's argument being considerably more stringent. Some individuals have speculated that this arose from the differing personalities of the two astronomers. These two formidable individuals significantly contrasted with each other. Oort was the preeminent Dutch astronomer of his time, respected and revered by his peers in the discipline. Zwicky was a contentious individual who relished challenging his fellow astronomers' firmly held scientific beliefs, irrespective of their nature. He was concisely both stimulating and frustrating. Nonetheless, an alternative perspective posits that Zwicky's findings, which required up to 50 times more dark matter than luminous matter, perplexed astronomers' understanding. Despite being aware of Zwicky's findings for the past 50 years, astronomers tend to dismiss them rather than acknowledge their significant implications. By the conclusion of the 1930s, two distinguished astronomical authorities asserted that dark matter constitutes a substantial fraction of the universe. Nevertheless, dark matter remained dormant for 4 decades, while notable astronomical discoveries and issues regarding luminous matter became more prominent. This included the evolution and rivalry between the steady-state and Big Bang theories regarding the universe's origin, and the discovery of pulsars, radio galaxies, and the most luminous objects in the universe, referred to as quasars. Quasars, the active cores of distant galaxies, rank among the most ancient entities in the universe. They are exceptionally luminous, emitting more energy than 100 supergiant galaxies. Black holes, and the cosmic microwave background radiation, a Big Bang remnant, were predicted and discovered. Notwithstanding their importance, all these discoveries have neglected the principal form of matter in the universe. In 1970, a discovery revived interest in dark matter, resulting in a surge of attention such that by the late 1980s, astronomers worldwide were conducting extensive studies of dark matter in individual galaxies. Oort posited that dark matter resided within the disks of galaxies. In contrast, Ken Freeman and his associates employed radio telescopes to investigate galactic rotation, ultimately providing the initial evidence that dark matter exists in extensive halos surrounding the centers of galaxies, including the Milky Way. By analyzing stellar movements, Oort, Lindblad, and Stromberg clarified the Milky Way's rotation. Subsequently, Oort quantified the motion of stars in a direction orthogonal to the galactic disk. This enabled him to ascertain the galaxy's mass, resulting in the erroneous inference that dark matter is concealed within the disk of our galaxy. What is the current status of other galaxies? What is their mass? And do they contain dark matter? Other galaxies are so distant that their star clusters appear as indistinct light patches to all but the most powerful telescopes, making it impractical to determine their mass by observing individual stars. An alternative is necessary. In the case of a spiral galaxy, the procedure is relatively straightforward. By measuring the collective rotation speed of the stars, one can calculate the necessary gravitational mass to preserve its structural integrity. In 1939, Horace Babcock sought to achieve this for the Andromeda galaxy, Galaxy M31. He quantified the Doppler variations at multiple locations along the periphery of the galaxy, and subsequently contrasted them with the galaxy's mean spatial motion to ascertain its rotational velocity. Translating the perceived velocity of a galaxy's edges into kinetic energy requires comprehension of the galaxy's true dimensions, which depend on distance and apparent size. Determining luminous matter necessitates understanding the galaxy's luminosity, which depends on its distance. During Babcock's observations, the distance to M31 was poorly comprehended. Ultimately, he misjudged its distance and dimensions, determining that the ratio of luminous mass to gravitational mass was 50. Although we now acknowledge this as erroneous, he was advancing in the appropriate direction. Babcock and his contemporaries were limited to observing the visible disks of galaxies. Nevertheless, the dark matter problem rapidly transcended this limitation. Observing the universe at alternative wavelengths was impractical. Therefore, all observations utilized optical spectral line shifting. Oort made substantial contributions to the progress of Dutch radio astronomy. Particularly, one of his students, Henk van der Hulst, forecasted the existence of the 21 cm line of neutral hydrogen, which was identified in 1951. This radio emission resembles the spectral lines of Oort and Zwicky, yet it emanates from neutral hydrogen gas in interstellar space rather than from stellar bodies. The electromagnetic spectrum, which includes radio and visible bands, adheres to the same physical principles. As a result, spectral lines in the radio spectrum experience equivalent Doppler shifts due to motion along the line of sight. The emission of the 21 cm spectral line from hydrogen gas within and around a galaxy, as opposed to from stars, represents a considerable advantage. It enables radio astronomers to quantify the Doppler shift and, consequently, the motions of various regions within a galaxy, even without stars, provided that the hydrogen gas is neutral or atomic. This study utilizes instruments like the Australia Telescope Compact Array. A hydrogen map of the galaxy records the Doppler shifts of radio waves emitted from diverse locations within the galaxy, facilitating the precise measurement of velocities throughout a hydrogen-rich galaxy. Galaxies displaying visible hydrogen are primarily spiral or irregular in morphology. If galaxies consisted solely of their visible components, the stars, and crucially the gas at the peripheries, would exhibit slower motion than the stars situated nearer to the center. The gravitational pull diminishes with distance from the galaxy's center, necessitating reduced velocity to counteract the inward attraction. A rotation curve is a graph depicting the rotational velocity of the galaxy about its distance from the center. In the absence of dark matter, a galaxy's rotation curve is anticipated to rise to a peak and then diminish, indicating that the rotational velocity decreases as one progresses toward the galaxy's edge. In the 1930s, Oort discerned the asymmetrical rotation of our galaxy. All parties concurred that the rotation curves of galaxies did not disclose any unforeseen results. In the 1960s, optical techniques measured various rotation curves by analyzing the ionized gas in the central regions of spiral galaxies. However, these rotation patterns do not apply to the galaxy's outer regions. No substantial insights were obtained until the 21 cm data was accessible. While investigating an unrelated matter, Freeman discovered that galaxies were not rotating as previously assumed. Spiral galaxies display a characteristic luminosity distribution, with brightness diminishing exponentially from the center to the edges. the underlying cause of which is yet to be elucidated. Freeman analytically derived the rotation curve for the galaxy and compared it with the established rotation data. The prevalence of hydrogen gas, which generally extends far beyond the observable limits, constrains the assessment of galaxy rotation curves. After the rotation data, we can quantify the mass within the ultimate measurable radius. In 1970, despite restricted observations of the rotation of other galaxies, Freeman discovered adequate evidence to stimulate his interest. He noted that the rotation curves of 3 or 4 galaxies displayed an erroneous shape, based on the assumption that the galaxies consisted exclusively of stars and gas. Their alignment with the projected curves was insufficient, as the observed rotation curves diverged from expectations. This suggests that stars and gas are not converging towards the center, but are intermittently exhibiting higher velocities. Freeman published an article asserting that there was undeniably a problem. He proposed that these galaxies harbored considerably more dark matter than luminous matter, yet the disks did not disclose this information. It must exist beyond the stars and gas, surrounded by a halo of dark matter that completely encircles the luminous galaxies. Recent 21 centimeter observations of the Andromeda galaxy, conducted concurrently by teams in the UK and US, confirmed the existence of an anomaly. Shortly after Freeman's announcement, another concept provoked astronomers' reflection. This concept, similar to Oort's studies, is deemed less relevant to the dark matter dilemma. However, it initially prompted astronomers to consider it seriously. In Film 3, we observed that Hubble classified galaxies based on morphology. We estimated that approximately 1/3 of the spiral galaxies displayed prominent or barred central structures. In 1973, astronomers Jeremy Oestreicher and James Peebles from Princeton University published a paper explaining the rarity of bar formation in spiral galaxies. What factors impeded the formation of bars in the majority of galaxies? During that period, individuals conducted computer simulations of spiral galaxies and noted that their models often formed central bars. Stars assemble because of their shared gravitational pull, and their sociable nature is contagious. A slight accumulation of stars will prompt increased clustering, attracting more stars and sustaining the cycle. Gravitational instability induces the formation of clumps. This instability transforms the galaxy into a bar shape, which is more stable than a uniformly distributed disk of stars. At that time, astronomers were oblivious that approximately 2/3 of spiral galaxies contain bars, leading to questions regarding the lack of bars in the remaining spirals. Oestreicher and Peebles argued that a significant halo of dark matter encircling a spiral galaxy could impede bar formation, as they posited that most spiral galaxies do not possess bars. This would reduce the gravitational impact of the stars on the galaxy's morphology. The stars would serve as test particles, delineating the configuration dictated by the dark halo. We now acknowledge alternative methods to impede bar development. One approach entails amplifying the random motions of stars in the inner regions of the disk, thereby disrupting their systematic circular paths and intensifying the chaotic movements of stars toward the center. In the 1980s, Freeman and his associates at Mount Stromlo Observatory and the University of Groningen quantified the stochastic movements of stars within the disks of various spiral galaxies, including our own Milky Way. Since then, astronomers have performed similar measurements on other spiral galaxies. The findings indicate that velocity dispersion, or the degree of randomness, is significantly greater in the centers of galaxies, preventing the formation of a bar structure. It is presently recognized that in most galaxies, the black halo is integral to the structure and dynamics of the outer regions, while the interior regions are predominantly influenced by the gravitational effects of stars. Oestreicher and Peebles correctly inferred that dark matter halos surround galaxies. albeit possibly not for the reasons they originally suggested. Although the pursuit of truth may seem chaotic or unstructured, it invariably transpires in science. The 1970s were a crucial period for the progress of dark matter research. Oestreicher, Peebles, and their colleague Amos Yahil synthesized the available dynamical evidence regarding galaxy masses, building upon their theories of dark halos. This led to the belief that large spiral galaxies, like our own, contain approximately 10-12 solar masses, substantially more than previously estimated. They utilized the neutral hydrogen rotation curves of three proximate spiral galaxies, M31, M81, and M101, identified by Morton Roberts and Arnold Rotz as evidence. They analyzed the motion of galaxy pairs and calculated the virial masses of small galaxy clusters. Published in 1974, their study provided essential data that greatly enhanced our comprehension of dark halos encircling galaxies. Their mass estimations approximate the most precise figures achievable today, 30 years later. Scientific discourse often notes that their conclusions coincide with those of others. In Estonia, Einasto and his colleagues Karsik and Saar similarly concluded that spiral galaxies must contain substantial mass in the same year. During the 1970s, Vera Rubin and her colleagues at the Carnegie Institution of Washington collected high-quality optical rotation curves for spiral galaxies, which generally displayed flat rotation curves. Flat optical rotation curves do not extend sufficiently from the galactic center to serve as definitive evidence of dark matter, thereby perpetuating discourse on the subject. However, the conclusive evidence emerged in 1978 when Albert Bosma presented a PhD thesis at the Kaptein Laboratory in Groningen. Utilizing the Westerbork radiosynthesis telescope, he generated 21-centimeter rotation curves for approximately 20 spiral galaxies, indicating that nearly all were situated at the peripheries of the 21-centimeter data. By the conclusion of the 1970s, it became evident that a significant issue existed. Either Newton's gravitational theory is erroneous, a notion to be discussed subsequently, or galaxies are enveloped by vast halos of dark matter. Nevertheless, the problem may be more significant. The rotation curves derived from 21 centimeters emissions indicate the galaxy's rotational velocity to the limit of hydrogen gas distribution. The probability of detecting further mass is considerable, as it lies beyond the observable limit of hydrogen. As a result, the inquiries continue. What is the scope of our investigation into the dark matter halo? Is there a technique to explore beyond the hydrogen disk of a galaxy? Examining the hydrogen distribution in spirals reveals a distinct edge. The density of hydrogen gradually decreases over distances of several kiloparsecs, before abruptly ceasing at the final kiloparsec. This transpires due to the lack of hydrogen, although it is simply that humans are unable to perceive it. What accounts for hydrogen's sudden invisibility? This is likely due to UV rays ionizing hydrogen. When an ultraviolet photon interacts with a hydrogen atom, it separates the positive nucleus, a single proton, from the negative electron. The origin of this UV radiation is unclear. Nevertheless, two separate theories exist. Quasars in outer space emit substantial UV light. However, rigorous limitations on their formation render this an inaccurate assertion. Another possibility is that most spiral galaxies display considerable star formation in their central regions, leading to significant ultraviolet radiation emission. How do the star-forming regions at a galaxy's core influence the hydrogen in its outer regions? Galaxies are primarily planar, and in a hydrogalaxy, the peripheral regions cannot directly observe the star-forming zones at the core, due to the significant dust in the inner regions that absorb ultraviolet radiation. Although galaxies appear flat, their edges are not consistently so. The hydrogen disk frequently warps, resulting in edges resembling the brim of a slouch hat. Jos Bland Hawthorne of the Anglo-Australian Observatory observed that this grants hydrogen in the galaxy's outskirts a more unobstructed perspective of the core areas where star formation transpires. This galaxy has been acknowledged for 25 years, and although warping of the stellar plane is rare, warping of the hydrogen layer is common. It is now understood that most galaxies display distortion. Although numerous studies exist regarding the origin of these warps, the reasoning behind their presence remains unclear. The dark matter halo may display a preferred plane of symmetry due to its slight flattening. If this plane is not parallel to the stellar plane, it will attract the hydrogen in the galaxy's outer regions toward itself. This will occur above and below the stellar plane, where the dark galaxy is elevated and the hydrogen is diminished. Nevertheless, it endures as a fundamental dynamical puzzle in astronomy, and despite the endeavors of some of the most brilliant minds, it remains unresolved. The hypothesis that hydrogen correlates with the star-forming regions in the galactic center is quantitatively superior to some alternative explanations of the galaxy. Nevertheless, this is highly innovative, and viewpoints will experience multiple alterations. One may inquire why only the peripheral regions of the galaxy experience this ionization. What inhibits the ionization of the visible disk in the hydrogen galaxy? The galactic core emits ultraviolet radiation that permeates the entire galaxy. Nevertheless, the ultraviolet photons of the galaxy can ionize only a limited amount before depleting. The upper layer of hydrogen absorbs ionizing photons in regions with plentiful hydrogen. The internal hydrogen remains neutral and is detectable owing to its shielding from ultraviolet radiation. In the galaxy's most remote regions, where hydrogen density is minimal, a threshold exists at which ultraviolet photons can ionize nearly all hydrogen and maintain it in this state. When this occurs, the detectable neutral hydrogen in the 21 cm line significantly decreases. This may elucidate the pronounced edge. However, it also signifies the existence of an ionized hydrogen region beyond the neutral hydrogen boundary detected by radio telescopes. A hydrogen ion undergoes recombination to maintain its ionization over time. When an ion, specifically a hydrogen nucleus or proton, interacts with an electron, they amalgamate and produce recombination radiation. A supplementary UV photon swiftly ionizes this neutral hydrogen atom. This recombination radiation is observable as a series of spectral lines. Amateur and professional astronomers distinctly identify the H-alpha line as the most significant hydrogen line visible from Earth. The H-alpha radiation originating from the outer regions of galaxies is extremely faint and was undetectable until recently. Advancements in spectrographs and the development of a Fabry-Perot interferometer have enabled astronomers to quantify minute levels of ionized hydrogen emission. In collaboration with Joss Bland Hawthorne and other associates, Freeman has performed observations utilizing the 3.9-meter Anglo-Australian telescope at Siding Spring Observatory in New South Wales. They have expanded the rotation curves beyond the limitations previously set by neutral hydrogen. The initial galaxy where this technique was utilized was the notable spiral NGC 253, and the method has subsequently been applied to M33, a distinguished spiral galaxy near the Andromeda galaxy. The extent of hydrogen's expansion determines the limits of this methodology. The direct observation of the dark matter halo is still elusive. We can enhance our observations beyond the atomic hydrogen threshold by employing satellite galaxies as indicators of the gravitational field. The erratic trajectories of these satellites around their host galaxy prevent them from descending into the parent galaxy. This enables us to utilize their movements to ascertain the galaxy's gravitational field up to several hundred kiloparsecs from its core. Denis Zwicky of the Galaxyard Observatory pioneered this methodology. The dark halos of spiral galaxies, including ours, reach up to 150 kiloparsecs. What insights can be derived about colossal elliptical galaxies following a discussion on spirals? Astronomers have deduced the existence of dark matter halos by examining the rotation curves of spiral galaxies. The trajectories of stars in elliptical galaxies are not wholly straightforward. What methods are employed to ascertain the mass of inactive, non-rotating galaxies? Various techniques are available for ascertaining the masses of elliptical galaxies. And, although none are as uncomplicated as those employed for spiral galaxies, two methods stand out significantly. One method is to observe the motion of distant objects within the halos of elliptical galaxies. We can quantify the distinct velocities of these entities, which may be planetary nebulae or globular clusters. Planetary nebulae are crucial in pursuing dark matter, necessitating a comprehensive analysis of these remarkable phenomena. We have noted how massive stars terminate their brief but brilliant existences in spectacular supernova detonations. Nonetheless, such stars are uncommon. Most end their existence as peacefully as they began. Billions of years after their formation in vast clouds of gas and dust, stars like the Sun conclude their life cycle peacefully, surrounded by luminous clouds that emit a subtle radiance in the universe. For a brief cosmological interval, these remarkable clouds in the sky provide scientists with insights regarding the future existence of Sun-like stars. Understanding stellar mortality began in the 17th century, when astronomers investigated the cosmos with large telescopes. Developed in the early 16th century, telescopes featured small lenses until the mid-17th century, revealing only the nearest and brightest celestial objects in the night sky. William Herschel was one of the foremost pioneers in astronomy. Herschel was an accomplished guitarist. However, his true passion resided in astronomy. Using a custom-built telescope, he examined the heavens for new, uncharted celestial objects. In 1781, he discovered Uranus, the first planet recognized since antiquity, whose erratic motions ultimately led to the discovery of Neptune, and constituted one of the earliest examples of identifying unknown dark matter through the behavior of observable matter. During their cosmic surveys, astronomers often observed small spherical gas clouds resembling planets. When viewed through 18th century telescopes, the appearance of these unusual objects may mislead an astronomer into thinking they have discovered a new planet or comet. Scrupulously observing the suspect was the exclusive technique employed to authenticate the identification of a planet. Planets orbit the Sun and change position relative to the stars from one night to the next. In contrast, the nebulae remain fixed about the stars. Herschel classified certain nebulae as planetary nebulae because of their superficial resemblance to planets. They fascinated him, and upon finding one with a faint star at its center, he became convinced that the nebulae were gaseous clouds surrounding a star. This was a notable revelation considering the scant comprehension of stars during that period, which was virtually absent. 2 centuries later, astronomers have corroborated Herschel's representation. A planetary nebula is a gaseous envelope surrounding a star approaching the end of its life cycle. All stars, including the Sun, produce energy via nuclear fusion, primarily transforming hydrogen into helium. The nuclear process produces substantial energy, some of which are arriving on Earth as light and heat. The star's core generates energy that adequately counteracts its substantial gravitational force, enabling it to continue expanding for billions of years. Nonetheless, the restricted availability of hydrogen fuel limits a star's longevity. Approximately 5 billion years post-formation, a star like the Sun undergoes a depletion of its hydrogen reserves. As the star radiates reduced energy, its core experiences contraction from gravitational forces. The increased density at the core enhances the star's energy production, expanding and cooling the outer layers. The star expands to a diameter several tens of times greater than that of the Sun. evolving into a red giant that exceeds the Sun's size by a factor of 100. The density augmentation at the core is sufficient to initiate helium fusion into oxygen and carbon. Hydrogen continues to be converted into helium within a shell surrounding the core. The star resembles an ovum, a helium core surrounded by a white hydrogen envelope. The star ultimately exhausts its helium. However, its mass restricts the combustion of oxygen and carbon, which produces heavier elements. Without outward rushing energy to maintain the star's expansion, its core undergoes gravitational collapse. Once again, the outer layers expand and cool while the star increases to several hundred times its original diameter. The core of the inflated star, which is in its final stages, contains half the mass of the Sun and is presently 1,000 times more luminous. A delicate stream of matter from the core travels at velocities of up to 20 km/sec. The expanding gas cloud, previously the star's outer layers, evades the gravitational influence of the core and drifts gently into space. As the gas disperses, it cools, becoming icy and concealing the star. After millennia, the core ultimately collapses, attaining temperatures of approximately 25,000 K. The star's intense radiation causes the surrounding gas to emit light, akin to the illumination of gas in a fluorescent tube when exposed to an electrical current. At its peak, the central star can reach a temperature of 200,000 K, possessing luminosity equivalent to 1,000 suns. The radiant gas has evolved into a planetary nebula featuring a brilliant central star and may persist for 100,000 years. Ultimately, the gas disperses, and the star no longer exists as a white dwarf. Notwithstanding their magnificence, planetary nebulae are transient structures in the universe. A typical planetary nebula may encompass up to 100,000 atoms within the volume of a sugar cube. In contrast, your air contains roughly 10 quintillion atoms within the same volume. The cloud is so fragile that changes in mass distribution within the star or the density of the surrounding interstellar medium can cause it to adopt atypical shapes. While most planetary nebulae display symmetry, only about 10% appear spherical. Planetary nebulae exist transiently, with their gaseous remnants dispersing for thousands of years. Nonetheless, their unique characteristic makes them prominent against the surrounding darkness. The physics of the gas surrounding the hot central star suggests that roughly 20% of the star's light is. It appeared as a significant emission line when emitted at a particular wavelength. This spectral line originated from doubly ionized oxygen, ODI, at a wavelength of 5007 angstroms in the blue region. This constitutes the green segment of the visible spectrum. This indicates that the luminosity of these diminutive stars at this particular wavelength surpasses that of their surroundings. Planetary nebulae function as indicators of the matter in neighboring elliptical galaxies. Globular clusters are an alternative to planetary nebulae due to their sufficient brightness for visibility in proximate elliptical galaxies. Nevertheless, a considerably large telescope is required to conduct this observation. Significant dark matter appears to surround elliptical galaxies, warranting investigation. These strategies fundamentally depend on an assumption regarding stellar motion, which is uncertain. The spirals illustrate that all phenomena are governed by cycles, which results in. Life seems simple. However, the mechanics of elliptical movements are ambiguous. An alternative, autonomous approach utilizes the phenomenon whereby many elliptical galaxies emit X-rays from heated gas in their outer regions. This gas is not in motion. It exists solely in chaotic disarray. Astronomers propose that this phenomenon arises from aging stars in distant galaxies releasing gas. The gas, driven by its velocity, is expelled into the interstellar medium, forming clouds that follow diverse trajectories and collide with gas from other stars, moving in opposite directions. The motion of the gas converts the previously stored energy into heat adequate to produce X-rays. X-rays frequently illuminate elliptical galaxies, enabling us to observe the distribution of hot gas and determine the requisite gravitational field to maintain it. A significant proportion of the elliptical galaxies analyzed in this manner are the prominent central galaxies situated at the cores of clusters. M87 in the Virgo cluster and NGC 1399 in the Fornax cluster are supergiant elliptical galaxies easily measurable due to their significant X-ray emissions, abundant globular clusters, and planetary nebulae. Examining the dynamics of globular clusters, planetary nebulae, and the distribution of hot gas is not the sole approach. However, both yield analogous outcomes. The structure of dark matter halos remains mysterious. They may be spherical or flattened, like a partially inflated beach ball. The sole certainty is the quantity of mass contained within a specified radius. The issue is compelling as simulations performed by astronomers regarding the formation of the early universe and halo dynamics consistently produce flat halos. The typical halo is primarily prolate, resembling a rugby ball, to a slight degree. To date, corroborating the concept through observation has proven exceptionally difficult. Freeman has engaged in such endeavors and can confirm that it is a disheartening process. One of the preliminary efforts to quantify the structure of the dark matter halo involved the study of polar ring galaxies. A ring of stars and gas encircles a conventional disk galaxy in these unusual galaxies, rotating in a plane perpendicular to the disk. Currently, 157 polar ring galaxies have been recognized, and although their formation mechanism remains unclear, they may result from the merger of two standard galaxies. The disk of the primary galaxy is distinctly identifiable, though it almost lacks the gas essential for galaxy formation. Star formation occurs in the perpendicular ring, sometimes involving several billion solar masses of neutral hydrogen. In 1983, Vera Rubin, Francois Schweizer, and Brad Whitmore published a pivotal study examining the velocities of matter in the polar ring of the galaxy AO 1360801. Analogous to the galactic disk, the rotation curve of the galactic ring exhibited a flat profile, resulting in the inference that galaxies are surrounded by dark matter that extends a minimum of 3 times beyond the visible perimeter of the galaxy. An exemplary case of this phenomenon is the galaxy pair NGC 4650A, which consists of 2 colliding galaxies that resemble 2 large perpendicular wheels with a common center. Astronomers believe that the presence of 2 galaxies in a circular formation, with their disks oriented in opposing planes, would assist them in determining the configuration of the dark matter halo surrounding them. Freeman was included among them. The objective was to ascertain the rotational velocity of galaxies in non-parallel planes. This would aid in comprehending the forces in those dimensions, and consequently, the quantity of dark matter present in those directions. Regardless of public expectations, the outcomes remain ambiguous, and despite the availability of superior data, interpreting their significance remains challenging. Diverse methodologies are available to duplicate the observed data. Magda Arnaboldi and Françoise Combe demonstrated that certain theories depict a planar, dark matter halo that may be aligned in various orientations, complicating the search for a definitive explanation. A supplementary technique astronomers utilize to determine the structure of dark matter. Halos entails analyzing hydrogen flaring within galactic disks. The hydrogen layer within a galaxy is not entirely planar. The central regions are level, while the outer sections extend outward, leading to greater thickness, likely attributable to the disk's diminished mass and gravitational effect. As a result, the hydrogen layer becomes denser in the peripheral regions of the galaxy. The structure of the dark matter halo markedly affects the degree of flattening. The halo of a flat galaxy exerts a stronger gravitational pull on hydrogen, attracting it toward the disk more than a spherical galaxy. Astronomers have attempted to formulate arguments regarding the abundance of hydrogen at varying distances from the galactic center. This technique initially seemed promising. However, it has yielded multiple solutions. As a result, astronomers have a significant advantage in understanding the structure of the dark matter halo. Verifying the precision of the cosmological models would be satisfying. The analysis of Project Macho's findings, a prominent dark matter investigation, depends on the structure of the dark matter halo, posing a considerable practical issue. We must recognize the presence of dark matter halos and their impact on galaxies. Astronomers have quantified the dark matter halos of numerous galaxies, demonstrating that dark matter exists in all galaxies. Our situation is not an anomaly. Contrary to Oort's initial observations, the Milky Way's dark matter is not located within the disk. Instead, it resides in a halo similar to that of other galaxies, a notion that would be more acceptable to numerous astronomers. What constitutes the foundation of our knowledge? The Sun is roughly 8 kiloparsecs from the galactic center and up to approximately 20 kiloparsecs. Similar rotational methodologies applied to other galaxies can yield analogous results. The rotation curve is constant at this distance, signifying the existence of a dark matter halo. A preliminary correlation is noted between mass and distance from the galactic center. Mass equals 10 billion solar masses multiplied by the radius in kiloparsecs. Galaxy utilizes the British billion, which is equivalent to 1,000 million. Thus, upon reaching a radius of 20 kiloparsecs, we approximate that there are around 200 billion solar masses within a diameter of 40 kiloparsecs, nearly 3 times the mass attributable to starlight. In conclusion, we have made significant progress in understanding the presence of dark matter within the Milky Way. Nonetheless, we encounter a barrier beyond roughly 20 kiloparsecs. As a result of the galaxy's rotation, all objects observed beyond the Sun's orbit are moving across our line of sight, with minimal components along that axis. Doppler shift measurements of stellar motions are predominantly inadequate in this context, requiring the exploration of alternative methodologies for quantifying the Milky Way. Rather than lamenting our existence in the galaxy, astronomers leverage it. We seek indicators beyond the 20 kiloparsec galaxy that will clarify the motion of matter, and thus the mass, surrounding the Milky Way. What lies beyond? This represents the stellar halo of the galaxy. This should not be confused with the dark matter halo, but rather with the galaxy's faint luminous halo, which contains some of the galaxy's oldest stars. Nevertheless, extensive searching within the halo for halo stars is unnecessary, as a few are readily available to us. The stars near the Sun belong to the galactic disk and orbit the galaxy with us. Nonetheless, a small fraction of stars, about 1 in 1,000, emanate from the galaxy. The luminous halo is a nearly spherical aggregation of stars exhibiting minimal rotation. Rotation sustains the disk, whereas the unpredictable motions of the stars within the luminous halo uphold its integrity. The dynamic and vigorous halo stars navigate the galaxy with remarkable energy. As a result of these unpredictable movements, specific stars will inevitably pass near the Sun by chance. They move rapidly. This clarifies the benefits of determining the gravitational mass of the galaxy. To determine the mass of the Milky Way, measuring the velocity of the swiftly moving galaxy in the solar vicinity is necessary, as is calculating the mass required to sustain its gravitational binding to the system. This is known as the escape velocity argument, based on the premise that they would have already left if these stars had reached the galaxy's escape velocity, the speed necessary to overcome the Milky Way's gravitational pull. The Milky Way's gravity captivates them, evidenced by their swift motion and proximity. What if the star is an interloper, rather than a member of the Milky Way? This is certainly a possibility. Stars exist in intergalactic space, as will be elucidated later in our examination of the nature of dark matter. However, we must acknowledge that if a star traverses the solar neighborhood within the galaxy's disk, it is highly likely that it is a member of the galaxy. Nonetheless, the escape velocity sets a minimum criterion for the mass of the galaxy. Notwithstanding the significant speed of galaxy stars, it may still be substantially lower than the galaxy's escape velocity. Stars moving at velocities around 650 km/s are observed within the Milky Way vicinity. Yet to escape the Milky Way's gravitational pull, a star must reach speeds of 800–900 km/s. However, such stars have either not been observed or may be non-existent. Another theory posits that hot stars from galaxies do not enter the solar vicinity. Consequently, the escape velocity argument may establish a lower boundary for each of those galaxies. The lower threshold is roughly 300 billion solar masses, indicating a 50% increase in the mass of the galaxy as determined by the rotation curves. What methods did scientists originally employ to identify galaxy halo stars on Earth? How can we differentiate them from the disk stars? Fortunately, multiple methods are accessible. One should identify nearby luminous halo stars, particularly when analyzing cooler stars. The primordial halo stars emerged before the galaxy's augmentation, with heavy elements generated by supernovae. As a result, they exhibit unique chemical properties. Specifically, they are metal deficient, signifying that their heavy element concentrations, calcium, magnesium, and iron, are below 1/10 of those in the Sun. Astronomers began analyzing multiple stellar spectra, searching for those with exceptionally faint spectral lines. This task is less challenging than it seems. A Schmidt telescope allows astronomers to simultaneously capture the spectra of multiple stars. Schmidt telescopes are distinctive instruments characterized by a conical form and a sky-facing aperture, smaller than the primary mirror. Nonetheless, their optical configuration enables the generation of distinct images across an extensive field of view. Thus, they are ideal for conducting all-sky surveys in relatively short time frames. We have previously noted that a spectrograph frequently disperses starlight into a spectrum to disclose its spectral lines. An enhanced technique employs a glass prism affixed to the telescope's front to identify a rare star type. These objective prisms are immense. A Schmidt telescope, such as the United Kingdom Schmidt telescope at the Anglo-Australian Observatory, would employ a 48-inch diameter prism at the front of the instrument. The objective prism disperses the incoming starlight before its impact on the film. This generates an image that displays the detailed spectra of multiple stars, with each spectrum indicating the chemical composition of a star. The resultant shot utilizes multiple methods to distinguish between metal-rich and metal-poor stars. One method involves analyzing the spectra. Many astronomers have conducted this examination. Superimpose a grid onto the image to guarantee that no stars are missed, and systematically examine each spectrum to identify metal-poor stars. A modern technique employs digital measurement instruments to detect and analyze the spectra on the photographic plate. Astronomers utilize a larger telescope to acquire a more detailed spectrum to verify the characteristics of a metal-poor candidate star upon its identification. Unfortunately, halo stars are extremely rare, and astronomers have recognized many objects that do not represent the elusive targets they seek. The profound interest of astronomers in metal-poor stars has driven this modernization, greatly simplifying the work. A supplementary approach for detecting halo stars utilizes their swift movement. The movement of a star along our line of sight is termed its proper motion, as elucidated in Film 1. This can be quantified by capturing two images of the same stars at the maximum feasible temporal interval, or more pragmatically by comparing a contemporary photograph with one taken considerably earlier, usually by another individual. Examining the relative positions of the stars reveals swift stellar movement. The higher the velocity of a star across the celestial plane, the more it will have shifted between the two recorded images. Some halo stars display observable motions in the sky of 0.5 arcseconds per annum or more. This may seem trivial. It is less than 3,500 times smaller than the diameter of the entire Moon, but it is not difficult to measure. The movement is significant in the larger context, arising from their swift passage through space. A rapidly moving star indicates two possibilities: nearby, as proximity increases apparent motion, or traveling through space at a high velocity. If it is the latter, it may be a halo star warranting further investigation. Frustrated by the postponement in the observational appearance of halo stars in the solar vicinity, some astronomers examined the luminous halo directly. The technique employed is identical to that utilized for identifying proximate metal-poor stars. Their considerable distance and low luminosity complicate the search for halo stars within the halo. Nonetheless, astronomers have detected them at distances of 100 kiloparsecs. Astronomers can determine the galaxy's mass and the dark matter proportion by examining its random motions. Astronomers examine stellar pressure in the galaxy's peripheral zones, providing insight into the overall mass. It contains approximately 500 billion solar masses, within an average radius of roughly 50 kiloparsecs. The rotational factors necessitate a mass increase of up to 2.5 times. The Andromeda galaxy is a crucial tool for assessing the total mass of the Milky Way, located beyond our galaxy. This notable galaxy, the largest in the local group, is a spiral different from ours. It is roughly 750 kiloparsecs distant and is the nearest significant galaxy to the Milky Way. Owing to its approximately 15-degree inclination from edge-on, it manifests as an oval-shaped nebulous illumination in the northern constellation of Andromeda. Witnessing such a phenomenon with our naked eye is indeed a privilege. The Andromeda galaxy and the Milky Way approach each other at a velocity of approximately 118 kilometers per second. This is unusual, as most galaxies are moving away from us due to the expansion of the universe. What is the reason for the convergence of the Andromeda galaxy and the Milky Way? The solution is gravity, indicating the existence of significant matter. The two galaxies emerged concurrently with various smaller galaxies that form the local group. Initially, Andromeda and the Milky Way diverged due to the expansion of the universe. However, their gravitational attraction was sufficient to halt and eventually reverse this divergence. This significant task requires determining the total mass between the two galaxies. In 1959, English astronomer Frans Kahn and Dutch astronomer Lodewijk Voltier, a protégé of Oort, formulated this methodology. The phrase timing argument is employed as it requires an assumption about the time needed for the two galaxies to overcome universal expansion and begin to approach each other. We must establish an age for the universe. If the cosmos is ancient, space has ample time to rotate and accumulate galaxies. This indicates that alleviating the recession required diminished mass. If the universe is young, there has not been enough time to achieve the same result, requiring galaxies to be more massive and to merge within a considerably shorter period. While Kahn and Voltier continued to ascertain the precise age of the universe, we can approximate it at approximately 18 billion years for illustrative purposes. The currently accepted age is 13.7 billion years, thus offering a conservative estimate of the total mass of the two galaxies. The combined mass of the two galaxies is 4,000 billion solar masses at this epoch. Our share is below 50%, approximately 1,500 billion solar masses. This is roughly 8 times the mass indicated by rotation curves and 15 times the mass proposed by the galaxy's luminous matter. Similar arguments can be applied to smaller galaxies approaching us, yielding unexpectedly analogous outcomes. These factors engender astronomers' confidence concerning their dark matter research within the Milky Way. A mass of 1,500 billion solar masses suggests that the flat rotation curve of the galaxy should extend beyond 100 kiloparsecs. This is not surprising given that the luminous stellar halo attains this distance, suggesting that the dark matter halo may extend similarly. The amalgamation of these arguments illustrates the aforementioned correlation between radius and mass. Our galaxy's radius is similar to its radius in kiloparsecs multiplied by 10 billion solar masses. This relationship remains consistent up to a minimum of 100 kiloparsecs. In this context, we have considerably greater knowledge of our galaxy than any other galaxy, primarily due to our unique position, allowing us to employ supplementary arguments. Most galaxies conclude the process upon exhausting the hydrogen required to assess rotation curves. The forecasts terminate. The ratio of the dark mass of our galaxy is a minimum of 20:1. Nevertheless, the analysis of typical spiral galaxies, including ours, produces considerably lower values, mainly because mass measurements become incomplete after hydrogen depletion. Hydrogen extends beyond the cosmos, yet galaxies extend considerably further. The observed rotation curves of typical spiral galaxies reveal a dark matter to luminous matter ratio between 1.1 and 5.1, with few notable cases nearing the ratio found in the Milky Way. Thus, the Milky Way serves as a more precise representation of the conditions of various galaxies. Smaller rotating galaxies yield similar results, indicating that the true dark matter to luminous matter ratio in galaxies is below 21. In recent years, astronomers have employed approximate galaxy to determine the dark matter ratio in the Milky Way, which is only adequate. Astronomers determined the actual velocity of space by analyzing the motion of the large Magellanic Cloud across the sky and correlating it with existing knowledge of motion along our line of sight. This alone does not reveal any information about the mass of the Milky Way. Nonetheless, another relevant factor is the interaction between the large and small Magellanic Clouds. The Milky Way's two largest satellite galaxies, the Magellanic Clouds, seem to serenely orbit their substantial spiral counterpart. These vast, brilliant, and magnificent galaxies embellish the dark southern heavens, augmenting the luminous band of the Milky Way. However, their serene exterior conceals a torrent of violence as their proximity to the Milky Way progressively destroys them. Evidence of their gradual yet inevitable decline is a series of hydrogen remnants indicating their path. The Magellanic Stream extends for tens of thousands of light-years, forming an extensive arc encompassing nearly 100 degraalas in the celestial sphere. The Magellanic Stream, designated as such, was discovered in 1976 by Australian astronomer Don Mathewson, the former director of Mount Stromlo and Siding Spring Observatories. Mathewson identified an extensive flow of neutral hydrogen gas trailing behind the two clouds, akin to the smoke emitted from a burning ship. The discovery of a considerable amount of gas escaping from the two galaxies has profound implications. The Magellanic Clouds were, in a sense, deteriorating. A galaxy employs hydrogen gas as its nutrient source to produce stars illuminating the galaxy. Nevertheless, stars are not everlasting and necessitate replenishment. Thus, if a galaxy's gas reservoir is exhausted, no material will be accessible to form new stars. The Magellanic Stream signifies the depletion of gas from the clouds, resulting in the impoverishment of the galaxies. The Magellanic Stream clearly indicates the destruction of the Magellanic Clouds. Yet the exact mechanism behind this occurrence remains unclear. Tidal theories propose that the stream results from a tidal interaction wherein the Milky Way's substantial gravitational force extracts matter from the Magellanic clouds. The alternative hypothesis is termed ram pressure stripping. The concept asserts that the stream is formed as the clouds move through the sparse gas surrounding the galaxy. Accumulating gas from the clouds, similar to long hair in the wind. The halo gas forms a heated corona that envelops the galaxy at a minimum distance of 70 kiloparsecs. The corona can be directly observed through the X-ray spectra of quasars. Until recently, it was difficult for most astronomers to determine which theory was correct. An important breakthrough in 1998 almost confirmed the tidal theory regarding the origins of the Magellanic Stream. The discovery transpired during the H.I. Parkes All-Sky Survey, HIPASS. This research investigates the southern sky for extensive structures beyond our galaxy loying, the 64-meter Parkes radio telescope, and the dedicated Parkes multi-beam facility. This undertaking is remarkable because of the extensive monitoring duration necessary. Utilizing a solitary radio telescope and receiver to survey the sky incrementally would necessitate a protracted duration. The Parkes telescope generally observes a restricted segment of the sky, about 1/4 the area of the full moon, making an all-sky survey like HIPASS a task that would have formerly necessitated 30 years. The Parkes multi-beam facility fundamentally transformed the circumstances. Its distinctiveness lies in its ability to observe vast areas of the radio sky and simultaneously analyze phenomena across multiple wavelengths. The extensive field capabilities derive from 13 radio feeds at the center of the large dish, in contrast to the singular feed employed by other radio telescopes. This enables observing 13 points within a field of view exceeding 1 degree. This allows astronomers to perform comprehensive radio surveys more swiftly than customary. The multi-beam facility accomplished the task in 3 years, rather than 30. A notable feature of the multi-beam facility is its ability to capture the spectra of radio objects, akin to the methods employed by astronomers with visible light for decades. Astronomers can quickly ascertain the redshift of galaxies, facilitating prompt computations of their recession velocity and distance. These two advancements produce a rapidly expanding three-dimensional map of galaxies, many of which have not been previously detected. HIPASS primarily surveys interstellar gas in galaxies beyond the local group. As the study advanced, it became apparent that the primary data contained significant information concerning gas proximity to the residents. Information regarding high-velocity clouds, HVCs, characterized by their rapid movement, was notably intriguing. The origin of HVCs remained unclear, leading the HIPASS team to commence a PhD research project to investigate the phenomenon. This coincided with the arrival of a new PhD student at Mount Stromlo Observatory, Mary Putman, an assistant professor at the University of Michigan. Her thesis program sought to clarify the distribution, origin, and environment of the HVCs. In the course of her endeavors, Putman made an unforeseen discovery. The region surrounding the Magellanic clouds is a compelling site for investigating neutral hydrogen, and she promptly analyzed and integrated the data regarding the Magellanic system upon its availability. The result was an abundance of new information and a compelling feature progressing ahead of the Magellanic clouds in the sky. The long-expected leading arm of the Magellanic Stream, as predicted by tidal theory. The initial observations suggested that the leading arm is significant, measuring no less than 25 degrees in length, nearly 1/4 of the trailing stream identified by Matthewson. The radio brightness is roughly 1/20th of the trailing stream. Therefore, if the trailing and leading streams are equidistant, which cannot be conclusively established, this brightness ratio reflects a mass ratio. This, however, does not present a problem for the tidal theory. The leading and following arms would be nearly identical if the tidal interaction were exclusively two-body. The interaction encompasses three celestial bodies, the two Magellanic clouds and the Milky Way, which disturbs the symmetry, as theorized. Various tidal theories explain the Magellanic stream. Certainly all will necessitate adjustments to incorporate the leading arm. Nonetheless, each of these theories implicates our galaxy employing these theories and the established space velocity of the large Magellanic cloud. One can estimate the mass of the galaxy inding to the large Magellanic cloud, approximately 50 kiloparsecs distant. The result is roughly 200 billion solar masses, marginally lower than standard estimates, yet significantly exceeding the luminous mass, and largely depends on understanding the Magellanic stream's formation. The large Magellanic cloud contains dark matter, and recent rotational analyses suggest a flat rotation curve. Such investigations are complex due to the system's disorganized and chaotic nature. The black halo of our galaxy Arcalzite, significantly influencing its rotation. It is transporting its dark matter halo through our galaxy, aiding confusion and ambiguity. In conclusion, it is not ideal for research purposes. In contrast to numerous galaxies of similar luminosity, such interactions do not compromise the study of dark matter in small, irregular galaxies. The Milky Way and its vicinity comprise the spiral galaxy, globular clusters, the two Magellanic clouds, and a group of satellite dwarf galaxies. This inventory, although orderly, is insufficient. If only a minor fraction of the galaxy rises luminous matter, it can no longer function as a descriptor for the Milky Way. Nevertheless, as demonstrated in the following film, the significant dark matter content of the Milky Way is negligible when compared to dwarf galaxies, where stars merely signify the existence of extensive concentrations of dark matter. Galaxies display a diverse range of forms and sizes. At one extreme of the galactic spectrum are colossal elliptical galaxies that primarily occupy the cores of galaxy clusters. These massive entities encompass 10^12 solar masses and exhibit diameters of up to 200 kiloparsecs. Larger galaxies, such as the Milky Way, are significantly more common. In contrast to large elliptical galaxies, representing about 1/5 of all galaxies, spiral galaxies account for 3/4 of all luminous galaxies in the universe. Spiral galaxies are rich in gas and dust, crucial for star formation, while elliptical galaxies predominantly contain older stars and have limited resources for new star creation. The remaining 5% comprises irregular galaxies lacking discernible shape or structure. These statistics omit a considerable quantity of galaxies. The incorporation of dwarf galaxies modifies the tally. Some dwarf irregular galaxies display gas and intermittent star formation, akin to spiral galaxies. Dwarf ellipticals are primarily lacking in gas. The population of dwarfs varies according to the environment. They are more abundant in clusters of galaxies, and less so in loose associations. Our local galaxy group is a typical loose collection comprising 4 spiral galaxies, no giant ellipticals, 20 dwarf irregular galaxies, and approximately 17 dwarf ellipticals. Some of the smallest and most ubiquitous dwarf galaxies are exceptionally dim and difficult to observe, even in extensive imagery. They consist of just over several million stars and a significant quantity of dark matter. The preliminary evidence that dwarf galaxies contain significant amounts of dark matter was discovered by Mark Aronson, a trailblazer examining dark matter halos in small galaxies. In 1987, a tragic incident led to the demise of Aronson, a distinguished astronomer, while he was operating the 4-meter telescope at Kitt Peak Observatory. He measured stellar velocities in several small galaxies, which was highly difficult. He measured merely 6 stars, yet observed an unexpectedly substantial velocity dispersion. This represents the variance in stellar velocities, which is a fundamental indicator of the pressure sustaining the expansion of galaxies and clusters. Astronomers viewed this conclusion skeptically. 6 stars do not provide a substantial measure of stellar pressure. Moreover, some astronomers postulated that certain stars might exist as binary systems. Orbital velocity is relevant when 2 stars orbit each other, as seen in a binary system. In a survey of stellar motions within a galaxy, one may observe 2 stars that belong to binary systems. Binaries typically consist of a luminous star and a faint, sometimes imperceptible companion. We may acquire a spectrum of the binary system, yet only detect the light and lines of the more luminous star, thus ascertaining its velocity. 2 binary systems within a galaxy may possess identical velocities. However, if the luminous star approaches the observer while the brilliant star in the other binary recedes, it creates the illusion of substantial velocity discrepancies. Over time, the spectral lines of both binaries will display oscillation across the spectrum, as each rotating pair of stars alternately approaches and recedes from the observer. However, if one examines a singular image of stellar motion, substantial discrepancies in velocities may be observed that do not accurately reflect the dynamics of binary systems. This dispute continued for years. However, there are samples of more than 100 stars in nearby dwarf galaxies. Despite extensive measurements, astronomers have not observed any spectral line variations anticipated from Aronson stars, which are binary systems. Astronomers now contend that the stars in these small galaxies display rapid motion, indicating the existence of dark matter. Recently, Ken Freeman and John Cormandy from the University of Texas collaborated to elucidate the distinctive characteristics of dwarf galaxies. They possess dark matter, with some exhibiting an exceptionally high quantity relative to their diminutive size. The 2 scientists have conducted extensive research on dark matter in dwarf galaxies. Several years prior, researchers discovered that the dark matter within these diminutive galaxies appears exceedingly dense. This prompted endeavors to accurately determine the dark matter densities of halos encircling galaxies with varying luminosities. Diverse individuals evaluated halo characteristics through different methodologies, requiring the standardization and refinement of the data. This required minimizing error sources, especially in establishing a dependable technique for measuring distances to galaxies, which remains persistently difficult. Upon completion, they revealed substantial correlations previously obscured by disordered data. Large spiral galaxies exhibit comparatively low dark matter densities, whereas smaller galaxies demonstrate increasingly elevated dark matter densities. Dwarf galaxies, similar to their larger counterparts, display a variety of shapes. Some smaller galaxies possess a higher volume of gas than others. When abundant gas is present, they display irregularity and a mottled appearance in their star-forming regions. Conversely, when oxygen is limited, they appear smooth and are commonly designated dwarf spheroidal galaxies. Dwarf irregular galaxies exhibit rotation akin to spiral galaxies, facilitating the measurement of their halo densities. The erratic movements of their stars predominantly support others, including the dwarf spheroidal satellites of the Milky Way. Irrespective of the dwarf galaxy type analyzed by the 2 researchers, the result was uniform. Small galaxies contain a significant quantity of highly dense dark matter. Indeed, the stars in specific galaxies constitute a trivial fraction of the overall mass. In the most extreme cases, the stars account for only 1/100th of the total mass. Investigating dwarf galaxies presents significant challenges. The reduced star density in specific smaller galaxies makes their faint luminosity almost undetectable in images. Due to their proximity, astronomers can determine the velocities of individual stars, employing telescopes such as the 3.9-meter Anglo-Australian telescope and the larger 8-meter telescopes in Chile and Hawaii. Assessing the velocity of specific stars requires the examination of their corresponding spectra. Astronomers employ multi-object spectrographs to concurrently analyze the spectra of multiple stars, as manually directing a telescope at each star would be impractical. For substantial celestial entities like adjacent dwarf galaxies, a system of optical fibers is commonly utilized to convey light from multiple stars into a spectrograph. The spectrograph disperses stellar light into a spectrum for examination. In the early iterations of these fiber optic systems, one end of each fiber was inserted into an opening in a metal plate fixed in the telescope's focal plane. Each aperture was meticulously positioned on the plate, forming a distinct star's image. Although fiber optics significantly enhance the efficiency of astronomical observations at night, which is crucial due to rising telescope time costs, substantial preparatory work is required to achieve optimal results. A microdensitometer is often necessary to ascertain the positioning of the fiber tips and capture an image of the galaxy. Precision remains imperative despite the arduous nature of this process and its susceptibility to errors. If we mismeasure the star's position, we will improperly attach the fiber to the plate, hindering its observational capacity. Microdensitometers are rare precision instruments valued at several $100,000 each. Microdensitometers illuminate a glass photographic plate, revealing the image of the galaxy G examined. The plate is calibrated in 2 dimensions with a precision of 1 millimeter in response to light. And although it operates like a traditional negative, fluctuations in light intensity represent the image of a star. Upon identification, we convert the positions of the stellar images on the plate into right ascension and declination coordinates. These instruments were formerly situated at Mount Stromlo Observatory and the Sydney offices of the Anglo-Australian Observatory. Unfortunately, approximately 13 years ago, the facility at Mount Stromlo was destroyed by a lightning strike, while the equipment at the Anglo-Australian Observatory became obsolete. Consequently, we must promptly send photographic plates to England for measurement. Australia and England formalised an agreement to facilitate this. In return for Australia's management of the UK Schmidt telescope at Siding Spring, British astronomers would catalogue and safeguard the photographic plates. In the preliminary phases of fibre systems, the positions of the stars were marked on a circular brass plate with a diameter of 40 centimetres and a thickness of 3 millimetres. We punctured the plate with tiny holes, each indicating the star's position upon its affixation to the telescope. Furthermore, larger apertures were excavated at the sites of more luminous guiding stars for fibre bundles, allowing scientists to accurately align the telescope with the galaxy H. Smaller aperture was reamed with a jeweler's reamer and fitted with a single optical fibre. After positioning the plate in the telescope, we connected the opposite ends of the fibres to a spectrograph. The Anglo-Australian Observatory was the first institution to utilise fibre optics in astronomy. The 2DF, or 2-degree multi-fibre spectroscopic survey facility, has become a significant instrument. The 2DF differentiates itself from its predecessor by employing a robotic mechanism to arrange the fibres on a reusable plate, instead of manually inserting them into a disposable brass plate. Furthermore, 2DF executes this function simultaneously with the telescope's operation. One plate encompasses 400 fibres in the telescope's image, whereas a second plate is configured with 4 additional fibres. Like an hourglass, a tumbler device secures each plate to its outer surfaces. After each observation session, the tumbler inverts, facilitating the entry of the second plate into the telescope's focal plane while displacing the first plate. The robot positioner adjusts the initial configuration after initiating the second set of fibres. All of this transpires at the summit of the 3.9-metre telescope. 2DF was conceived and constructed by individuals from the AAO. Its primary function is to map redshifts and ascertain the distances of galaxies by constructing 3-dimensional models of the universe's structure. The achievements of AAO scientists and engineers prompted the European Southern Observatory to engage them in developing a fiber positioner for their 8-meter Very Large Telescope in Chile. The fiber positioner is presently functional. Nonetheless, let us return to the topic of dwarf galaxies. At night, astronomers orient the telescope towards the sky, calibrate the guide stars, and initiate their observations. At night, astronomers direct the telescope towards the galaxies. Astronomers generally execute several brief half-hour exposures rather than one extended exposure. This incremental method allows for the systematic refinement of the data. A notable problem with CCDs is their vulnerability to cosmic rays, high-energy particles originating from various directions in the sky, leading to information contamination. Such errors are significantly simpler to correct by consolidating multiple, brief exposures. Although it necessitates careful planning, the system operates remarkably well. After the evening, each fiber will have contributed to generating a star's spectrum. Astronomers can determine a star's velocity about a reference star of known speed by examining its spectra. Implementing this procedure for all specified stars produces a depiction of the velocity distribution alongside the quantity and distribution of mass. Cormandy and Freeman compiled data on dark matter across 43 galaxies, ranging from the most luminous spirals to the faintest known dwarf galaxies. Their research validated and quantified the correlation between the number of stars in a galaxy and the volume of dark matter present in that galaxy Oort indicates that smaller galaxies possess a greater proportion of observable dark matter. The Milky Way is a significant galaxy, with more than 90% of its mass consisting of dark matter. However, in the smallest galaxies with a sparse star distribution, dark matter represents an even larger fraction of the total mass. Intermediate brightness elliptical galaxies constitute an exception to this rule, exhibiting approximately 20% of the Milky Way's luminosity. Observations of planetary nebulae at significant distances from their centers suggest they contain little to no dark matter. The causes of the substantial disparities among intermediate ellipticals are still unidentified. Furthermore, while massive galaxies like the Milky Way contain larger amounts of dark matter due to their total mass, dark matter is significantly more concentrated in dwarf galaxies. The most diminutive dwarf galaxies are difficult to observe due to their sparse stellar populations. The central dark matter density is approximately 1 solar mass per 30 cubic light-years, which is 100 times greater than the dark matter density in a giant galaxy, and significantly exceeds the density of stars and gas in the Milky Way's disk near the Sun. These fragile galaxies may seem delicate, yet they more closely resemble cannonballs. These connections provide new insights into the impact of dark matter on galaxy formation. They elucidate the increasing evidence that the smallest galaxies, such as the dwarf spheroidal orbiting the Milky Way and possessing a millionth of its luminosity, are surrounded by substantial dark halos. Astronomers were uncertain whether such significant dark halos in these small galaxies were typical, anomalous, or a misinterpretation of the observations. Recent observations suggest that dwarf galaxies typically exhibit a high density of dark matter, irrespective of being classified as dwarf spheroidal or gas-rich dwarf irregular galaxies. What accounts for the significant quantities of dark matter present in these ostensibly fragile galaxies? The elucidation lies in the observation that the faintest dwarf galaxies are nearly unchanged remnants from the primordial era of galaxy formation. A dwarf galaxy signifies a remnant of the universe from a remote period, possibly when it was only 1 to 3,000 of its current age and significantly dense. This signifies the commencement of galaxy fragmentation. Theoretical frameworks suggest that smaller galaxies formed before larger ones. Most of the fragments merged to create progressively larger galaxies. However, this process led to a substantial increase in orbital energy within the emerging massive galaxies, caused a dispersion of matter, resulting in a decrease in density. The dark matter density in the Milky Way is roughly 1,000th that of a dwarf galaxy. Nonetheless, the colossal galaxies did not incorporate all the dwarf galaxies. The diminutive galaxies observed today successfully avoided assimilation. The explanation for the high densities of dwarf galaxies suggests that dark matter, whatever its true nature, is likely primordial material from the universe's inception. This aspect makes the study of dwarf galaxies an intriguing field of research. The correlations of dark matter challenge the prevailing theory concerning the formation of most dwarf galaxies. Certain astronomers propose that dwarf galaxies are formed due to the collision between two large galaxies. Gravitational waves are said to extract elongated streams of gas and stars from their parent galaxies as they propagate. And small clusters of gas and stars within these streams can coalesce under gravitational influence, enabling them to endure the collision and resemble diminutive galaxies subsequently. This is rational, and some dwarf galaxies may arise in this manner. But is it the predominant method? The area surrounding our galaxy is a suitable site for investigating this type of tidal relic, owing to the interaction between the Milky Way and the large and small Magellanic clouds, as referenced in the preceding film. Distinguishing between tidal dwarf galaxies and primordial dwarfs should be straightforward, as large galaxies possess dark halos with low densities that extend existing structures. Consequently, we anticipate that tidally formed dwarfs will exhibit reduced dark matter concentrations compared to their progenitor galaxies. The smallest dwarfs demonstrate markedly higher dark matter densities than the Milky Way or the Magellanic clouds, suggesting they are authentic galaxies from the early universe, rather than simple tidal remnants. This suggests that the prevalence of dwarf galaxies is unaffected by the limited number of galaxy collisions since the emergence of large galaxies. Dwarf galaxies may exhibit a higher ratio of luminous matter to dark matter, owing to the reduced gravitational forces that hold their components together. The supernova explosions of primordial dwarf galaxies eject substantial amounts of gas upon the death of the earliest stars. The explosions have a negligible effect on dark matter, resulting in small galaxies retaining inadequate gas for star formation, producing low star counts despite high dark matter densities. Astronomers have long acknowledged that small galaxies vastly outnumber large galaxies, indicating that many more remain to be discovered. Astronomers have detected dwarf galaxies using the same microdensitometers utilized in their preliminary research. The locations of stars on historical photographic plates assisted British astronomers in determining their density. They also observed small clusters of faint stars that ultimately revealed genuine connections. Conversely, they designated these entities as galaxies. The smallest dwarf galaxies contain so few stars that they are difficult to observe among the stars of the Milky Way, and significantly harder to identify. Computational analyses of stellar positions have enabled recent discoveries of dwarf galaxies. To the human eye, no discernible connection exists among the stars. A hierarchy of these satellite galaxies presently exists. Some satellite galaxies are visible to the naked eye in celestial photographs, while others are nearly imperceptible. Before computer analysis, sky images near the suspected galaxy have no identifiable star formations. However, the existence of the galaxies is validated by measurements of the stars' velocities, demonstrating their collective motion through space. The extrapolation of the trend indicating an increase in dark matter in increasingly smaller galaxies implies the existence of galaxies with an extremely low stellar population, making them primarily composed of dark matter. Estimates indicate that dark galaxies measure a few hundred light-years in diameter and possess masses below 10 million solar masses. Predictably, such items are exceedingly difficult to find. As previously stated, one approach employs computational searches to detect exceptionally low star densities. Another method may entail seeking subtle signs of hydrogen gas. The concluding film depicted the HIPAS survey as a potential source for such discoveries. The primary aim of the multi-beam system was to locate galaxies concealed by the Milky Way. These galaxies are obscured at visible wavelengths because their light is absorbed by the gas and dust in our galaxy. However, low-frequency radio waves, including 21 cm radiation, traverse the Milky Way without obstruction. As a result, radio telescopes like Parkes can clearly detect gas-rich hidden galaxies that are imperceptible to optical observatories. The multi-beam facility's extensive multispectral perspective facilitates the rapid and precise mapping of gas-rich galaxy locations. Recent multi-beam survey results revealed that optical telescopes had missed multiple galaxies beyond the Milky Way. We now comprehend that these galaxies are situated along sheets and filaments that link to observable entities on either side of the Milky Way. Following the analysis of merely 2% of the data from the multi-beam survey, researchers discovered numerous dwarf galaxies in the nearby universe. Most dwarfs are unclassified, faint dwarf irregular galaxies, discernible in optical sky photographs once their positions are established. This represents a substantial discovery. Dwarf galaxies, due to their abundance relative to larger galaxies, may provide a more precise indication of matter distribution in the universe, including the ubiquitous dark matter. The existence of dark matter in dwarf galaxies raises a crucial and unresolved question. Why are globular clusters lacking in dark matter? The rationale for the dark matter conundrum originates at the galactic level. However, astronomers are baffled as to why dark matter is unobservable at scales smaller than galaxies. This presents a conundrum, as there is no evident rationale for the lack of dark matter in globular clusters. Large globular clusters have a mass similar to the smallest dwarf galaxies, roughly 10 million solar masses. Nevertheless, their diameter is approximately 1/10 that of a typical dwarf galaxy. They navigate the dark matter halo of the Milky Way. When gaseous clouds converge, they compress to high densities, leading to the formation of globular clusters. The formation process, therefore, involves only ordinary matter and omits dark matter. This is especially puzzling given that most globular clusters in our galaxy are among the earliest known objects in the universe, forming simultaneously with the smallest dwarf galaxies, primarily composed of dark matter. We have now concluded our investigation of dark matter in the universe. We commenced our investigation with Oort's purportedly erroneous discovery of dark matter in the galaxy's symmetry. Subsequently, we examined the substantial quantities of dark matter in galaxy clusters and the dwarf galaxies encircling the Milky Way. Nonetheless, a final and undeniably significant source of evidence for dark matter requires examination before we can summarize the dark matter composition of the universe: gravitational lensing. Massive objects can distort spacetime are Einstein's general relativity core principle. Celestial bodies, including planets and stars, navigate the cosmos, rendering it as tangible as this volume. Just as one can bend and fold paper, significant objects can distort the fabric of space, similar to manipulating the paper on which these words are inscribed. The dimple is a funnel-shaped depression with sloping edges that become level 1 distance from the center. The Earth does not remain fixed to the Sun like a ball on a string. Rather, it orbits the edge of a gravitational well, similar to a marble on a roulette wheel. Upon discovering general relativity, British astronomer Arthur Eddington promptly recognized its importance and began preparing to assess its predictions, considering it unusual at that time and currently. One of its predictions was that light did likewise as matter followed paths of least resistance in spacetime. This concept was not especially innovative. Newton's classical theory posited that light would refract upon traversing a significant medium. He perceived light as mass particles, allowing him to calculate the amount of deflected light. The distortion of light by gravity contradicts Newton's theory. Einstein's concept is adequately clear to explain. Envision yourself aboard a spacecraft, liberated from all gravitational influences. Secured to one wall of the vessel to inhibit buoyancy, you grasp a torch that illuminates the opposing wall. When the vessel is stationary, the light beam follows a linear trajectory to the cabin's opposite wall, striking the surface at the same height from the floor as the flashlight. Activating the rocket engines will accelerate the vessel. Although light propagates at an extraordinary velocity, its speed is not limitless. This signifies that the ship has moved slightly when a photon emanates from the torch, crosses the ship, and strikes the opposite wall. The photon will subsequently strike the cabin wall near the floor, below the height from which it originated. When viewed from the side, the light beam resembles a descending arc of water flowing from a hose. Although Einstein could not express it with precision, he suggested that there is no difference between an accelerating vessel in space and a stationary vessel on a planetary surface. Gravity and acceleration are equivalent phenomena. The significant implication is that a gravitational object will bend light, analogous to a beam from a flame in a rising elevator. Has anyone validated this theory? Eddington acknowledged that the divergence would be negligible even in a significant gravitational field, leading him to choose the most massive object, the Sun. He chose to employ the stars rather than a torch. The theory asserts that light from background stars aligned with the Sun would be refracted, thereby modifying their apparent position, akin to a celestial mirage. The difference would be negligible, approximately 2 arcseconds at the Sun's periphery, akin to the size of a period at a distance greater than 100 meters. What methods can we employ to observe stars near the Sun? Generally, we issue invitations to them. What methods can be employed to observe stars near the Sun? The Moon obscures the Sun during a solar eclipse, making the stars visible in the darkened sky. This would allow Eddington to photograph stars near the Sun and compare their apparent positions with their known fixed locations. Eddington organized 2 expeditions to observe the total solar eclipse of 1919, assigning one team to the island of Principe, situated off the west coast of Africa. Eddington dispatched the supplementary mission to northern Brazil. We sent 2 expeditions to northern Brazil. We orchestrated 2 expeditions, anticipating that if one team encountered cloud cover during the eclipse, the other would benefit from clear skies. However, both teams experienced favorable weather conditions. We examined the photographs from both teams and determined that Einstein's predictions closely corresponded with the displacement of the star images adjacent to the Sun. Eddington publicized his findings in November 1919. The public viewed them as a significant confirmation of Einstein's hypothesis. The refraction of stars conferred fame upon Einstein. Today's observations yielded minimal results, as the deflections were approximately equal to the measurement errors on the photographic film. Subsequently, researchers have reproduced the data with increased accuracy, corroborating Einstein's prominence. It is understood that matter warps spacetime, and light follows this curvature. Generally, the curvature is minimal, leading to a perception of stars and planets in the nocturnal sky as stable and unchanging. The distinction is evident when the alignment of a substantial object and a distant light source is sufficiently proximate. Gravitational lensing, the phenomenon by which massive objects alter the trajectories of light waves, is a crucial instrument in the quest for dark matter. Maintaining appropriate distances between a distant luminous object and an intervening gravitational body will result in the distortion and magnification of the distant object's image. This is analogous to how conventional reading glasses focus light rays on a focal point. Gravity serves an equivalent purpose. If it deflects individual light beams, it can also redirect bundles of rays, converging them to a focal point. When one maintains focus, one acquires an image, an amplified, distorted depiction of the background object. A gravitational lens is an intervening entity that distorts light through gravitational magnification. Gravitational lensing fundamentally relates to mass and geometry. The deflection angle of a light beam traveling from a point mass to the focus is dictated exclusively by the object's mass and the ray's spatial proximity. The deflection is typically minimal. Consequently, extensive cosmological distances are required to produce an image at a specific location utilizing a gravitational lens, akin to a low-powered eyeglass lens, with an extended focal length. The ideal arrangement requires uniform distances between ourselves, the lens, and the background source. A lensing effect would be unobservable if we were positioned too near either the lens or the background source, notwithstanding the implausibility of such a situation. Nonetheless, we ought to observe an effect provided the distances are cosmological, at least 1 billion light-years, and the ratio between the two remains relatively low. Typically, there is no complete alignment between a distant object and a gravitational lens. This produces an arc-shaped representation of the object that is difficult to discern. When a distant point mass, an observer, and a gravitational lens are collinear, the lensing effect will produce a perfect ring centered on the gravitational lens. The radius of the ring is termed the Einstein radius. Despite the inadequate alignment of most gravitational lenses, we can ascertain the Einstein radius of particular arcs. What is the importance of this? By quantifying the Einstein radius via the arc's shape and dimensions, we can ascertain the mass of the lens. The implications of dark matter investigations are apparent, and we will discuss them shortly. Classical literature on gravitational lensing often cites the Einstein radius. Can the Einstein radius be observed in the sky when measured in seconds of arc? The MACHO project examines the interactions between background stars, point light sources, and stellar mass gravitational lenses. We measure these Einstein radii in micro-arcseconds, hence the term microlensing. Naturally, the arcs are too diminutive to detect. However, this does not negate the amplification of light. MACHO was specifically engineered to identify augmented light rays reaching the telescope due to lensing, yielding brighter images. The Einstein radius for clusters can vary from several arcseconds to 20 arcseconds, attributable to the considerable distances and substantial masses of the clusters. The observed lensing in the sky is contingent solely upon the mass of the lensing object, provided it is sufficiently compact. A larger object results in a greater gravitational distortion. The compelling aspect for dark matter researchers is that the extent of deviation is solely contingent upon mass, enabling the determination of a gravitational lens's mass by measuring the deviation magnitude. This method's elegance lies in its ability to determine mass without dependence on assumptions or theories. This matter is unequivocal. General relativity accurately forecasts the extent of deflection associated with a particular mass. Comprehending the geometry, the distances between the source and the lens, as well as the observer and the lens, is essential. Any mass can bend light and thereby serve as a gravitational lens. The only question is whether we can perceive the curvature. This pertains to the field of astronomy. Proximal objects, such as the Sun, cause a slight discernible deflection, while more remote stars within our galaxy warp the light from stars behind them. The crucial factor in all these scenarios is the alignment or proximity of the background light source and the foreground object to our line of sight. A veil of stars obstructs our observation of the galaxy, enabling us to perceive more remote background objects. Furthermore, the entire galaxy motion leads to the gradual movement of its individual stars across the sky, albeit at a relatively slow rate, as perceived from Earth. Considering the numerous stars in the visual field, some will likely align with a more remote object, examined two clusters of galaxies aligning in more distant occurrences, creating a unique situation. Indeed, as elucidated in Film 3, both Einstein and Eddington considered the probability exceedingly low. They concluded that although the concept was intriguing, it lacked practical utility in real life. Einstein published the concept of gravitational lensing in 1936. Zwicky hypothesized that gravitational lensing would be detectable if a galaxy aligned with the line of sight of a more distant entity, such as a quasar. Quasars serve as luminous background light sources, owing to their brightness and typical visibility at significantly greater distances than ordinary galaxies. In Film 3, Zwicky expanded on this concept by asserting that galaxy gravitational lensing is feasible and would serve as a potent method for determining the quantity and distribution of dark matter within the foreground cluster. This transpires when a proximate galaxy or cluster applies pressure on a remote quasar. Zwicky was correct, even though the first identification of a gravitational lens occurred 60 years after Eddington's famous eclipse experiment. Moreover, gravitational lensing is an effective technique for assessing the masses of galaxy clusters. Galaxy clusters are among the most densely packed collections of matter in the universe, situated within highly compact spatial areas. They are diminutive relative to the distance from background light sources, indicating their complete adherence to the previously discussed gravitational lensing principles. The universe is rich in galaxies, particularly those that are remote. Imagine a cone enveloping the cluster, with us positioned at the apex. Beyond the cluster, this cone encompasses a considerable volume of space, increasing the probability of encountering a galaxy or several galaxies that may be lensed. As we venture deeper into space, we encounter an increasing number of galaxies, providing a plentiful array of background light sources. Astronomers frequently observe strong lensing in wealthy galaxy clusters, resulting in multiple images of background objects. Magnification will augment one or more photographs, making them appear brighter than normal, whereas some multiple images may seem dimmer. Strong lensing presents a potential resolution to a significant issue in cosmology, determining the contentious Hubble constant, as illustrated in Film 2. Establishing the Hubble constant has presented a considerable challenge for astronomers over the past century. Hubble established that the farther a galaxy is, the faster it recedes. This transpires because each receding from all other galaxies. When observing two galaxies, one located behind the other, the nearer moving away from our perspective, the distant galaxy recedes at twice the velocity of the nearer one because of its movement away from us. It operates reciprocally. The inhabitants of either of the other two galaxies will witness precisely the same phenomenon. All galaxies in the universe are moving away from each other due to cosmic expansion. In 1929, Hubble evidenced this phenomenon and computed an initial rate of 200 km/s per megaparsec. Galaxies receded from us at an additional 200 km/s for each megaparsec of increased distance. However, he miscalculated the distances to the galaxies, leading to a substantial reduction in estimates of the Hubble constant once their true distances were established. The instrument named after him, the Hubble Space Instrument, has determined the figure to be a widely accepted 72 km/s MPC. Does gravitational lensing substantiate this figure? We previously observed that a factor affecting gravitational lensing is the distance to the lensing cluster, which depends on the velocity at which the cluster is receding from us. The Hubble constant is the variable that links these two important values. Diverse light rays produce multiple images, each following a unique trajectory from the source to our eyes. Given that each path possesses a distinct length, if the background source is a quasar exhibiting brightness fluctuations over months to a year, the disparity in brightness among the various lensed images can be utilized to ascertain the distance of the quasar from the observer or the path lengths. The phase difference characterized as the variation in arrival time at the peak or trough brightness of the two images, depends on the Hubble constant. It facilitates the measurement of the Hubble constant, rendering lensing an alternative method to ascertain this significant value. Understanding the lens comprehensively is fundamental, as it depends on its modeling. None of the systems analyzed to date exhibit a simple point mass, somewhat complicating the situation. The findings indicate that the Hubble constant is measured at a low value of 50 to 60 km/s MPC. However, they exhibit considerable uncertainty concerning the lens's attributes. Nonetheless, it offers a compelling perspective on the matter. And, in a domain where every technique has its constraints, an innovative, independent method is greatly valued. Weak lensing is more prevalent than strong lensing, despite being more difficult to detect. This does not produce multiple photographs, but rather distorts the image of the background light source. Weak lensing distorts the morphology of the background object. This phenomenon is not easily observable. It can only be discerned statistically by analyzing the configurations of numerous photographs captured in the same direction in the sky and identifying deviations from a straight line. This distortion would be perpendicular to the line connecting the object's image and the center of mass, leading to the distortion. A thorough examination of images primarily obtained from the Hubble Space Telescope, augmented by superior terrestrial data, has identified this phenomenon. Resolution is essential for detecting these subtle image distortions. Strong lensing is significantly more pronounced, and historically the first identified strong lens system was the double quasar 0957Pl561. Astronomers have been investigating uniquely blue quasars, particularly in the ultraviolet spectrum. Dennis Walsh's team captured an optical image of the quasar 0957Pl561, revealing two proximate stellar-like images approximately 5.7 arcseconds apart. For those familiar with the telescopic view of the binary star, Alpha Centauri comprises approximately 1/3 of the distance between the components. The acquisition of a spectrum from this object revealed its notable redshift, classifying it as a quasar. They performed a spectral analysis of the second object, as it was likely just a foreground star within our galaxy. The two objects exhibit identical spectra and share the same redshift. The closeness of two quasars may be coincidental, as binary quasars exist. The two photographs exhibited analogous variations in luminosity over time, with one image's alteration occurring 420 days after the other. This was substantiated by extensive investigations over an extended period. The images required to illustrate a unique quasar must have been substantially lensed by a foreground object, presumably a galaxy or a cluster of galaxies. This is a remarkable occurrence, primarily due to the infrequency of quasars being lensed in this fashion, with a discovery rate of roughly 1 annually. In contrast, the strong lensing of galaxy clusters is markedly more common, with Abell 2218 as one of the most notable examples. This prosperous galaxy cluster, located approximately 3 billion light-years distant, became notable when captured by the Hubble Space Telescope in 1994. The image originates from a study carried out by a consortium of astronomers from 4 universities: Warwick Couch, University of New South Wales; Richard Ellis and Jean-Paul Canaib, Cambridge University; Ian Smale, Carnegie Institution of Washington; and Ray Sharples, University of Durham. It is now one of the most exemplary examples of robust gravitational lensing ever recognized. The employment of the Hubble Space Telescope to investigate distant clusters was motivated not by gravitational lensing, but by the examination of galaxy morphology, their shapes and structures. We identified the galaxy cluster as experiencing substantial evolution. The galaxies displayed a markedly bluer tint and were experiencing star formation. The astronomers sought optimal photographs from the ground to determine the structural characteristics of distant galaxies. However, the galaxy's significant distance and small size made morphological details frustratingly elusive. The determination was reached that the exclusive means to fully comprehend galaxy morphology was to employ a space-based observatory, free from the distorting effects of the Earth's atmosphere, the Hubble Space Observatory. A resolution significantly surpassing that attainable on Earth would enable a new realm of research in clarifying the anatomy of distant galaxies. We have established that dense clusters of galaxies often display significant lensing effects. Astronomers utilizing the Hubble Space Telescope observed one in the initial cluster. The image's configuration resembled an L, featuring at least two images positioned at its center. The asymmetrical pair of images, which were mirror reflections of each other, signified the existence of a gravitational lens. The scientists quickly realized they could simultaneously investigate the morphology of distant cluster galaxies and comprehensively analyze gravitational lensing. The Hubble Space Telescope can detect gravitational lenses, measure their mass, and examine dark matter. Scientists obtained the initial photographs before the Hubble Space Telescope's repairs 1992. Notwithstanding the telescope's impaired state, its capacity for this type of work was remarkable, and it was clear that it would have a favorable future post-repairs. The team's time allocation to observe numerous high redshift clusters afforded them a competitive advantage over the wider astronomical community. The team resolved to enhance forthcoming observations to examine galaxy morphology and optimize the advantages of gravitational lensing. Ground-based imagery identifies Abell 2218 as a potent gravitational lens. The substantial gravitational field has distorted and intensified background galaxies' images, 3 to 4 times farther away, into numerous elongated and faint arcs. It was a prominent object for space exploration. Therefore, it was designated as one of the targets. The image of Abell 2218 was taken with the Wide Field Planetary Camera 2 in September 1994. The astronomers were astonished upon receiving the image, oblivious to its forthcoming grandeur. It displays the foreground galaxy cluster and a remarkable array of luminous arcs, distorted images of distant galaxies encircling the foreground cluster. It has since become a standard, a quintessential illustration of a gravitationally lensed cluster. After the Abell 2218 image, the team continued analyzing galaxy morphology and engaged experts in lensing analysis. The lensing analysis is intricate, because galaxy clusters are not simply point masses, but extensive mass distributions. Ellis and Smale conducted ground-based surveys to identify potential indicators of arcs that may signify substantial gravitational lensing. A substantial sample of clusters exhibiting lensing evidence was identified. Jean-Paul Kneipp, a French postdoctoral researcher at Cambridge, was tasked with modeling Abell 2218 and examining the lensed images of the cluster. Before joining the team, Kneipp had devoted his entire research career to this endeavor, adequately preparing him for the task. He possessed the software on a computer to analyze the clusters, rendering him an exceptionally qualified candidate for participation. The subsequent analysis of Abell 2218 produced 2 results. We must first engage in trial and error to ascertain the bulk distribution of the cluster. Initially, we developed a model of the lens informed by the light distribution evident in the photographs. The luminous matter is a preliminary indicator of the potential distribution of the underlying dark matter. Subsequently, a computer simulates the behavior of multiple light rays, originating from various background objects as they pass through the cluster, a method called ray tracing. We refine the model until it precisely replicates the original image. The Hubble Space Telescope images provide significant data, allowing us to constrain the model. We apply further adjustments until the model precisely replicates the image. This method enables an accurate delineation of the characteristics of the gravitational lens. The Hubble Space Telescope image of Abell 2218 significantly enhances this research by depicting a rare occurrence: the appearance of multiple images of different galaxies. 7 unforeseen composite images were uncovered. Gravitational lensing enabled the assessment of the galaxy cluster's mass via each set of multiple images. This phenomenon arose because each image had a unique impact parameter: the distance between the line of sight passing through the lens, the background object, and the image. This distance varies according to the mass of the intervening object. As the light rays from each background galaxy traverse divergent paths through the foreground cluster, each evaluates the foreground cluster's mass independently. Thus, it becomes possible to determine the mass between the image's apparent position and the actual line of sight. The existence of multiple images positioned differently from the foreground cluster's center is crucial. With articles visible at various locations within the image, measuring the foreground cluster's mass at different distances from the center becomes feasible. The second outcome from the image was determining the distance to the background galaxies. The lensing equations depend on the overall geometry, specifically the distances between the source, the lens, and the observer. Redshift observations can easily determine the distance to the lensing cluster. However, the distance from the lensing cluster to the background source remains indeterminate. Once we ascertain the lens characteristics through computer simulations, as previously outlined, we can calculate the distance to the background galaxies. By knowing the distance of the background galaxies from the lens, and consequently from ourselves, one can ascertain the duration since the light departed from the background galaxies, the look-back time. This enables an understanding of the properties of galaxies during that epoch. Following acquiring this esteemed image, astronomers have determined the distances of 120 objects, facilitating the evaluation of galaxies 50 times fainter than those observable by terrestrial telescopes. Thus, a gravitational lens is a monumental telescope investigating entities that would otherwise remain undetected by even the most advanced ground-based instruments. Without gravitational lenses, distant galaxy clusters would be barely visible. However, lenses such as Abell 2218 amplify their visibility by factors ranging from 10 to 50. The remote galaxies beyond Abell 2218 are located at a redshift of 1-2, signifying their existence when the universe was less than half its current age. The discovery of Abell 2218 advanced the study of dark matter and catalyzed significant research, resulting in the imaging of numerous affluent galaxy clusters with the Hubble Space Telescope. Gravitational lensing provides persuasive evidence that dark matter constitutes most of these clusters. Investigations employing gravitational lensing have demonstrated that 90% of the clusters predominantly comprise dark matter. Despite cluster variations, luminous matter represents less than 15% of the total cluster mass. Lensing clusters exhibit dark matter similar to galaxies, although it may be more densely concentrated at the center than luminous matter. Gravitational lensing is an effective technique for probing dark matter. It avoids complex physics and extraneous variables, allowing for a direct estimation of the foreground cluster's mass, encompassing both luminous and dark components. Gravitational lensing images also accurately depict the luminous matter within the foreground cluster. By juxtaposing the lensing mass with the luminous mass, we can ascertain the cluster's mass-luminosity ratio and quantify the dark matter present. Although clusters are not simplistic point masses but intricate systems containing hundreds of galaxies within a dark matter halo, certain assumptions regarding dark matter distribution must be established. We have sufficiently refined the theoretical framework to produce highly accurate measurements.